Nuclear engineering megaprojects are reshaping how the world generates power for the future. From next-generation reactors and massive containment systems to ultra-secure facilities built with microscopic precision, these projects combine extreme safety demands with some of the most complex engineering ever attempted. In this documentary, we break down how these nuclear megaprojects are built, the technologies driving them forward, and why they could redefine global energy for decades to come. Let's discuss Plant Vogtle, a nuclear power plant located in Burke County, Georgia, in the United States. It is the largest nuclear power facility in the country, boasting a total capacity of 4,536 megawatts. Named after Alvin Vogtle, a former chairman of Alabama Power and Southern Company, the plant represents a blend of innovation, ambition, and engineering resilience. Plant Vogtle initially consisted of 2 Westinghouse pressurized water reactors, with Units 1 and 2 coming online in 1987 and 1989, respectively. These reactors were designed with General Electric steam turbines and electric generators, each offering a capacity of 1,215 megawatts. Their construction marked a significant investment jump from an estimated $660 million to $8.87 billion, a figure adjusted to $19 billion today. Despite these cost overruns, the Nuclear Regulatory Commission extended the licenses of both units to 2047 and 2049, ensuring their longevity. In 2009, plans to expand the plant with 2 additional reactors began, utilizing advanced Westinghouse AP1000 technology. These reactors incorporate passive safety systems and modular construction methods designed to improve efficiency and safety. Units 3 and 4 were equipped with nearly 600-foot-tall natural draft cooling towers, enhancing their cooling capabilities. However, the construction faced significant hurdles, including contractor delays, the 2017 bankruptcy of Westinghouse, and escalating costs. Originally budgeted at $14 billion, the project's costs ballooned to $34 billion by 2023. Unit 3 achieved commercial operations in July 2023, making it the first nuclear reactor in the US in 7 years. Unit 4 followed suit in April 2024, marking the completion of the ambitious expansion. The AP1000 reactors employed at Vogtle are cutting edge, featuring passive safety systems that can automatically cool the reactor core in emergencies without operator intervention. The cooling towers for these reactors are nearly 600 feet tall, making them among the tallest in the world. Advanced machinery like modular construction systems and robotic welding tools ensured precision but added complexity to the project. With the capacity to power over 1 million homes, it showcases the potential of nuclear power as a sustainable energy source. What set the Darlington Small Modular Reactor project apart from the beginning was its use of a fully licensed, pre-developed nuclear site, something exceedingly rare in the nuclear industry. The Darlington Nuclear Generating Station in Ontario had long maintained a site preparation license for future expansion, which streamlined early regulatory processes for the Small Modular Reactor, or SMR. This advantage allowed project teams to initiate earthworks and enabling infrastructure much earlier than would typically be possible for a new nuclear build. Initial site development began with large-scale excavation to accommodate the reactor island, turbine structures, and support facilities. Rock blasting and removal were required to reach the design depth for seismic and flood protection. The site lies near Lake Ontario, so hydrological modelling informed the grading strategy and stormwater detention systems. Extensive cut and fill balancing was undertaken to minimise material export and optimise the site's profile for future service roads and vehicle access. Subsurface characterisation was essential for the foundation design of the SMR. Geotechnical boreholes and core sampling provided detailed profiles of the limestone bedrock and glacial till overlay. Once the excavation reached bedrock, foundation work began with rock anchors, concrete mud slabs, and waterproofing layers. The nuclear island foundation required a heavily reinforced concrete mat slab designed to distribute high concentrated loads from the reactor vessel and containment structures. The SMR selected for Darlington is a pressurized water reactor with integrated steam generation and passive safety features. The reactor building is being constructed using modular components prefabricated off-site, including sections of the containment structure, equipment modules, and piping skids. These modules are shipped by rail or specialized trucks and assembled using heavy lift cranes on engineered laydown pads adjacent to the foundation. The modular approach dramatically reduces on-site labor requirements and improves quality control by shifting fabrication into controlled environments. Containment and auxiliary buildings use thick reinforced concrete walls with embedded steel liners and seismic isolation joints. Key safety systems, such as the passive heat removal system, emergency core cooling, and spent fuel cooling, are embedded in compact configurations to allow for the SMR's reduced footprint. Embedded conduits, grounding grids, and shielded penetration sleeves are installed in formwork before concrete is poured, ensuring precise alignment and shielding performance once complete. The turbine island, located adjacent to the reactor building, is built on deep foundations and houses the generator, condenser, feed water heaters, and auxiliary equipment. Although the power output of an SMR is smaller than traditional nuclear units, the turbine equipment must still meet exacting standards for steam quality, thermal cycle efficiency, and vibration performance. Heat rejection is handled through mechanical draft cooling towers with high-efficiency fans and drift eliminators, positioned to avoid fogging and icing in prevailing wind conditions. Grid connection infrastructure includes switchyards, step-up transformers, and control systems, all housed in electromagnetically shielded buildings. A centralized control facility oversees both reactor and balance of plant systems, using digital instrumentation and control platforms with redundant safety class architectures. In the quiet countryside of southern France, surrounded by pine forests and rolling hills, there's a construction site unlike any other on Earth. It's not another dam or bridge or skyscraper. It's a machine built to recreate the power of the sun. This is ITER, the International Thermonuclear Experimental Reactor, and it represents one of the most ambitious scientific collaborations in human history. The goal here is nothing short of mastering nuclear fusion, the same reaction that fuels stars, and turning it into a practical source of energy for our planet. The concept sounds simple in theory, but has pushed the limits of engineering for decades. Fusion happens when two light atomic nuclei, usually forms of hydrogen called deuterium and tritium, collide at extremely high temperatures and fuse into helium, releasing enormous amounts of energy. The problem is that replicating those conditions on Earth means creating and controlling plasma that's hotter than the core of the sun, about 150 million degrees Celsius, and keeping it stable long enough to extract useful power from it. That's where ITER comes in. At the heart of the project is the tokamak, a donut-shaped reactor designed to contain the plasma using magnetic fields so powerful they could lift aircraft carriers. The machine itself is a masterpiece of precision. Its vacuum vessel weighs over 5,000 tons. Its superconducting magnets are cooled to near absolute zero, and every component must align with millimeter accuracy, despite being the size of a small building. The idea is that when the system is fully operational, the reactor will produce 10 times more energy than it consumes, something no fusion experiment has ever achieved before. What makes ITER truly remarkable is how global it is. It's being built through a partnership of 35 nations, including the European Union, China, the United States, Russia, Japan, India, and South Korea. Each partner contributes different components, from cryogenic systems to magnet coils to diagnostic sensors, and all of them have to fit together perfectly when assembled in France, Coordinating that kind of international supply chain is an engineering feat in itself, with massive pieces of hardware shipped across oceans and transported by custom-built convoys that crawl through rural roads to reach the site. The scale of the infrastructure around the tokamak is equally astonishing. There's a massive cryoplant to cool the magnets, a system of vacuum pumps, cooling water loops, radio frequency heating systems, and an entire electrical network dedicated to feeding the experiment's colossal appetite for power. When ITER begins its first plasma runs, it will consume more electricity than a medium-sized city, though the aim is to prove that fusion can eventually produce far more energy than it uses. Yet the challenge isn't just technical, it's also philosophical. Fusion has been called the energy of the future for over half a century, and ITER's success or failure could finally determine whether that future is real. If it works, it could open the door to commercial reactors that generate clean, virtually limitless energy from seawater, with no carbon emissions and almost no radioactive waste. But for now, ITER remains an experiment, a monument to human cooperation and scientific persistence, standing quietly in Provence as thousands of engineers and scientists work to capture the power of the stars here on Earth.
Let's head to France to explore the Flamanville nuclear reactor project. Located in the Normandy region, the Flamanville 3 reactor is part of the larger Flamanville nuclear power plant, which already includes 2 operational reactors. Construction on the Flamanville 3 reactor began in 2007. This project is a flagship for the European pressurized reactor technology, developed by Framatome and Électricité de France. The ITER is an advanced design aimed at increasing efficiency and safety in nuclear power generation. However, the road to completion has been anything but smooth. Originally slated to be operational by 2012, the project has encountered numerous delays and cost overruns. The estimated cost of Flamanville 3 has ballooned from an initial $3.3 billion to over $13 billion. This makes it one of the most expensive nuclear projects in Europe. The delays have primarily been due to stringent safety requirements, technical challenges, and regulatory changes, each adding layers of complexity to an already intricate project. Flamanville 3 is designed to generate approximately 1,630 megawatts of electricity, enough to power about 1.5 million homes. The reactor utilizes ITER technology, which features a double-layered containment structure to prevent radiation leaks and a core catcher to contain the reactor core in the event of a meltdown. One of the major engineering challenges of the Flamanville 3 project has been the quality control of materials and construction. For example, in 2015, it was discovered that some of the steel components in the reactor vessel had higher carbon content than specified, potentially affecting their strength and safety. This required extensive testing and, in some cases, replacement of parts, further delaying the project. Despite these setbacks, significant progress has been made. The reactor building, towering over 200 feet high, houses the most advanced nuclear technology available. The control room is equipped with cutting-edge systems to monitor and manage reactor operations in real time, ensuring the highest standards of operational safety. The project is now estimated to be completed by mid-2024. Let's shift our focus to Norway and delve into the fascinating Snøhvit LNG project, an ambitious energy initiative set in the Arctic region. Located in the Barents Sea, this project is Norway's first liquefied natural gas development, representing a significant leap in the country's energy capabilities. The project began with the discovery of the Snøhvit gas field in 1984. It took nearly 2 decades of planning and development before production finally commenced in 2007. This groundbreaking project is notable for its remote location and the challenges associated with Arctic conditions. One of the most remarkable aspects of the Snøhvit project is the decision to construct the LNG processing facilities onshore on Melkøya Island, near the town of Hammerfest. Natural gas extracted from the Snøhvit field is transported through a 90-mile subsea pipeline to Melkøya, where it is processed and cooled to -260 degrees Fahrenheit to be converted into liquid form. The total cost of the Snøhvit project is estimated at around $8 billion. The onshore facility on Melkøya includes Europe's largest LNG liquefaction plant, which has the capacity to produce nearly 5.7 million tons of LNG annually. This facility also includes storage tanks, loading berths, and other essential infrastructure, making it a comprehensive and self-sufficient operation. The plant on Melkoya employs cutting-edge technologies to reduce emissions and energy consumption. One notable feature is the carbon capture and storage system, which captures CO2 from the natural gas and injects it back into a reservoir beneath the seabed, preventing it from entering the atmosphere. Despite its successes, the Snøhvit project has not been without challenges. The harsh Arctic climate, with its extreme cold and long periods of darkness, poses unique operational difficulties. Ensuring the safety of workers and maintaining the integrity of equipment in such conditions require rigorous planning and robust engineering solutions. In addition to its technical achievements, Snøhvit LNG has strengthened Norway's position in the global energy market. The LNG produced at Melkoya is exported to various countries, including those in Europe and Asia, enhancing energy security and providing a cleaner alternative to coal and oil. This project has also paved the way for future Arctic developments, showcasing the feasibility and benefits of harnessing resources in remote locations. Let's investigate the Płock complex located in Poland next. This project involves the construction of new production units, storage facilities, and support infrastructure to enhance the complex's output and efficiency. Construction of the complex began in 2020, with it being completed in 2023. The project represents a significant investment, estimated at around $3 billion. One of the primary objectives is to increase the production of ethylene and propylene, which are essential feedstocks for the chemical industry. These products are used in the manufacturing of plastics, synthetic rubber, and other industrial materials. The complex features state-of-the-art production units equipped with advanced technology to ensure efficient and environmentally friendly operations. The project includes the construction of a new steam cracker, which will break down hydrocarbons into ethylene and propylene using high-temperature steam. This process is critical for producing the raw materials needed for various chemical products. The new facilities will incorporate energy-efficient technologies and systems to reduce emissions and minimize environmental impact. The project also includes measures to manage waste and water use, ensuring that the complex operates in an environmentally responsible manner. One of the challenges of the project has been coordinating the construction activities while ensuring the continued operation of the existing facilities at the Płock site. The project team has employed advanced project management techniques to plan and execute the construction, minimizing disruptions and ensuring that the project stays on schedule and within budget. Next up, we have to travel to the United Arab Emirates, where the desert sands of Abu Dhabi hold the Barakah nuclear power plant. Located in the sparsely populated Al Dhafra region, this $24 billion megaproject aims to diversify the country's energy portfolio while meeting the region's growing power needs. Construction of the power plant began in 2012, spanning a 9-square-kilometer site along the western coast. The plant comprises 4 APRA-11400 reactors, each designed to generate 1,400 megawatts of electricity. Collectively, these reactors will produce a staggering 5,600 megawatts, meeting up to 25% of the UAE's energy needs and preventing the release of 21 million tons of carbon emissions annually. That's like taking 4.5 million cars off the roads each year. With a containment dome rising nearly 60 meters above ground and the reactor pressure vessel weighing over 500 tons, each reactor stands as a colossal feat of precision engineering. The reactors are built with multi-layered safety systems, including double-walled containment structures to withstand natural disasters and external impacts. But constructing a nuclear power plant in such a region was not without its challenges. The unforgiving desert climate required innovative cooling systems to maintain optimal reactor temperatures. Advanced desalination plants were built to supply millions of liters of cooling water daily, while engineers worked tirelessly to meet stringent safety and quality standards. By bringing in global expertise, the country ensured that the project met international best practices in nuclear safety. In a part of the world where oil has long been king, the power plant is setting the standard for nuclear energy, particularly in a geopolitical landscape often defined by energy challenges. When all 4 reactors are fully operational, Barakah will produce more electricity than many countries generate in a year. The Dunkirk LNG terminal in France is a critical infrastructure project designed to enhance the country's energy security and diversify its sources of natural gas. Located in the port of Dunkirk, The terminal has a capacity to handle up to 13 billion cubic meters of natural gas per year, making it one of the largest LNG terminals in Europe. The project includes the construction of storage tanks, regasification units, and support infrastructure to import and process liquefied natural gas. The construction of the storage tanks is one of the most complex aspects of the project. Each tank is designed to store LNG at a temperature of -260 degrees Fahrenheit, requiring advanced cryogenic engineering and materials. The tanks are double-walled structures with an inner steel tank surrounded by an outer concrete shell. The space between the two walls is filled with insulation to maintain the low temperature and prevent heat ingress. The regasification units are responsible for converting the LNG back into its gaseous state for distribution through the national gas network. These units consist of heat exchangers and vaporization systems that use seawater or ambient air to warm the LNG. The construction of these units involves the installation of advanced piping systems and control equipment to manage the flow and pressure of the gas. In addition to the storage tanks and regasification units, the project includes the construction of a jetty to accommodate LNG carriers. The jetty is equipped with unloading arms and safety systems to transfer the LNG from the carriers to the storage tanks. The construction of the jetty involves extensive dredging and piling works to create a stable foundation in the marine environment. One of the significant challenges of the Dunkirk LNG terminal project is ensuring the safety and security of the facility. The terminal is equipped with advanced safety systems, including gas detection, fire suppression, and emergency response equipment to protect workers and the surrounding communities. Additionally, the project must adhere to strict environmental regulations to minimize the impact on the marine ecosystem and air quality. We have to move over to Finland next for the Hanhikivi 1 nuclear power plant. Located in Płock, the project involves the construction of a new nuclear reactor, which will provide a stable and reliable source of electricity for the region. Construction of the Hanhikivi 1 nuclear power plant began in 2015, with completion expected by 2029. The project represents a substantial investment, estimated at around $7 billion. The plant will feature a Russian-designed Vver 1A200 reactor, which is known for its high safety standards and efficiency. The reactor will have a capacity of 1,200 megawatts, enough to power around 1 million homes. One of the primary challenges of the Hanhikivi 1 project has been ensuring compliance with Finland's stringent nuclear safety regulations. The project team has worked closely with regulatory authorities to ensure that the plant meets all safety requirements and is constructed to the highest standards. This includes rigorous testing and quality control measures throughout the construction process. The Hanhikivi 1 nuclear power plant will incorporate advanced safety features, such as a double containment structure, an emergency core cooling system, and a passive heat removal system. These features are designed to ensure the safety of the plant and its surrounding areas in the event of an emergency. The project also includes extensive environmental monitoring and mitigation measures to protect the local ecosystem. Nuclear power is a low-carbon energy source, and the plant will play a crucial role in helping Finland achieve its climate goals. By providing a reliable and stable source of electricity, the plant will reduce the country's dependence on fossil fuels and contribute to the reduction of greenhouse gas emissions. The construction of the Hanhikivi 1 nuclear power plant involves the use of advanced engineering and construction techniques. The project team has employed state-of-the-art technology to manage the complex logistics of building a nuclear power plant, including the transport and installation of large and heavy components. Let's talk about the Johan Sverdrup oil field in Norway next. Located approximately 87 miles west of Stavanger, the project involves the construction of multiple offshore platforms, pipelines, and support infrastructure to extract and transport oil from the field. Development of the Johan Sverdrup oil field began in 2015, with production starting in 2019. The project represents a substantial investment, estimated at around $17 billion. The oil field has estimated reserves of 2.7 billion barrels of oil equivalent, making it one of the most significant discoveries in the North Sea in recent decades. The construction of the Johan Sverdrup oil field required advanced engineering and construction techniques to address the challenges of operating in the harsh and unpredictable North Sea environment. The project features a network of platforms, including a processing platform, a riser platform, and a living quarters platform, all connected by bridges to create an integrated offshore complex. The foundation work for the platforms involved driving large steel piles deep into the seabed to ensure stability. Each pile was installed using specialized pile driving equipment capable of operating in deep water. The piles were then filled with concrete to enhance their load-bearing capacity and resistance to corrosion. Heavy lift vessels played a crucial role in the construction process. These vessels transported large prefabricated modules, including topsides and jackets, from fabrication yards to the installation site. The use of heavy lift vessels allowed for the efficient transport and precise placement of these massive components. Each platform was equipped with advanced drilling and processing equipment, designed to maximize efficiency and minimize downtime. The installation of pipelines to transport oil and gas from the field to onshore facilities was another critical aspect of the project. These pipelines were laid using specialized pipelay vessels, which can handle the complex seabed topography and ensure the integrity of the pipeline system. The Johan Sverdrup oil field is expected to produce oil for several decades, contributing significantly to Norway's energy production and economic growth. It's time to travel to the coast of Kuwait, where the Al-Zour refinery is located. This enormous oil refinery is one of the largest of its kind, with a capacity to process 615 zillion barrels per day, fueling not just Kuwait's energy ambitions but also global markets. The sprawling site covers over 14 square kilometers, making it comparable to 19 football fields in size. The Al-Zour refinery, with an estimated cost of over $16 billion, was conceived to refine Kuwait's heavy crude oil and produce low-sulfur fuel oil that will meet international emission standards. The facility is not only impressive in its size, but also in its engineering, which has required innovative construction methods to build the 6 main refining units that house some of the world's largest processing equipment. Construction began in 2015, and by 2022 the refinery started its first phase of operations. The plant's advanced technology enables it to produce ultra-low sulfur diesel, kerosene, and naphtha. This not only bolsters Kuwait's refining capabilities, but also addresses international demands for cleaner fuel alternatives. The Al-Zour refinery is part of Kuwait's broader Clean Fuels project, which aims to overhaul its energy sector by providing environmentally friendly fuel. But constructing this colossal project wasn't without its challenges. The desert terrain posed difficulties in laying out the vast network of pipes and electrical infrastructure. The logistics of transporting enormous equipment to the remote site required careful planning, as some components like the distillation columns and reactors weighed over 500 tons each. To tackle this, a purpose-built port was established nearby to accommodate large cargo ships. The refinery employs a sophisticated control system that integrates automation and data analytics, providing real-time monitoring of every stage of the refining process. The Punta Sierra wind farm in Chile is an impressive renewable energy project located in the Coquimbo region, near the city of La Higuera. This project is designed to harness the strong and consistent winds of the coastal region to generate electricity. With a total installed capacity of 82 megawatts, the Punta Sierra wind farm is capable of producing enough energy to power approximately 60,000 homes. The construction of the wind farm involves several critical components, including the wind turbines, foundations, and the electrical infrastructure needed to connect the farm to the grid. The wind turbines, each with a capacity of 2 megawatts, are manufactured by leading companies in the wind energy sector. These turbines are mounted on towers that are approximately 260 feet tall, allowing them to capture the stronger winds at higher altitudes. The installation of the wind turbines requires meticulous planning and precision engineering. Each turbine consists of multiple components, including the rotor blades, nacelle, and tower sections, which are transported to the site and assembled using large cranes. The foundations for the turbines are constructed using reinforced concrete, designed to support the weight of the turbines and withstand the forces exerted by the wind. In addition to the physical construction, the project also involves the installation of an extensive electrical infrastructure. This includes the construction of a substation and the laying of underground cables to connect the turbines to the substation. The substation is equipped with transformers and switchgear to manage the flow of electricity and ensure a stable connection to the national grid. The Tanger Med port expansion in Morocco is a major infrastructure project aimed at transforming the port into one of the largest and most modern in Africa. Located on the Strait of Gibraltar, Tanger Med is strategically positioned to serve as a key hub for maritime trade between Europe, Africa, and the Americas. The expansion project includes the construction of new container terminals, logistics zones, and support infrastructure to significantly increase the port's capacity and efficiency. The construction of the new container terminals involves extensive dredging and land reclamation to create additional space for the terminals and berths. The dredging operations are carried out using specialized vessels that remove sediment from the seabed, allowing larger ships to access the port. The reclaimed land is then stabilized and prepared for construction using advanced geotechnical techniques. The new terminals are equipped with state-of-the-art cargo handling equipment, including gantry cranes, automated stacking cranes, and conveyor systems. These facilities are designed to handle the latest generation of ultra-large container ships, significantly increasing the port's throughput capacity. The construction of the terminals involves the installation of heavy-duty concrete foundations and the erection of steel structures to support the cranes and other equipment. In addition to the container terminals, the expansion project includes the development of extensive logistics zones and support infrastructure. These areas are designed to accommodate warehousing, distribution centers, and other logistics services, enhancing the port's role as a regional logistics hub. The construction of these facilities involves earthworks, concrete pouring, and the installation of utility networks to support the operations. One of the significant challenges of the Tanger Med port expansion project is coordinating the construction activities while keeping the existing port operations running smoothly. The construction teams must work closely with port authorities and operators to minimize disruptions and ensure the safety of workers and cargo. Additionally, the project must adhere to strict environmental and safety regulations to protect the marine environment and the surrounding communities. It's time to travel to New York next, where the Fulton Center project is located. Officially opened in November 2014 after years of meticulous planning and construction, this transit hub exemplifies the renaissance of New York City's commitment to efficient and user-friendly public transportation infrastructure. Spanning a full city block, the Fulton Center integrates 5 subway stations and 9 subway lines, facilitating the seamless flow of over 300,000 daily commuters. This impressive facility was built at a cost of approximately $1.4 billion, a reflection of its scale and the complexity of its design. The center itself is an architectural marvel, highlighted by the sky reflector net, an awe-inspiring art installation and engineering masterpiece that anchors the facility. This structure is an integrated artwork composed of 952 aluminum panels that brilliantly capture and disperse natural sunlight throughout the atrium, reducing the need for artificial lighting and creating a vibrant, inviting atmosphere. The construction of the Fulton Center was laden with challenges, notably the need to modernize and interconnect a labyrinth of century-old subway stations and infrastructure without disrupting daily transit operations. This task required innovative construction techniques and the extensive use of computer simulations to plan and execute each phase of development meticulously. The main building spans about 180,000 square feet, with additional space connecting the various subway entrances, exits, and passageways extending further underground. The complexity of its design and the integration of so many transit lines make the Fulton Center comparable to other major transit hubs like Tokyo's Shibuya Station. One of the unique aspects of the Fulton Center's construction involved the historical preservation component. Part of the project included the restoration of the nearby Corbin Building, an 1889 landmark, which was intricately woven into the fabric of the new transit hub. It's time to talk about the Pengerang Integrated Petroleum Complex next. This sprawling complex, which covers an area of over 20,000 acres, represents one of the largest investments in Malaysia's history, with an estimated cost exceeding $27 billion. Launched as part of Malaysia's economic transformation program to establish the country as a dynamic industrial hub in Asia, the project began its journey in 2012. It's strategically located at the southern tip of peninsular Malaysia, near international shipping routes, making it an ideal nexus for the trade of petroleum products. The refinery is designed to process 300,000 barrels of crude oil per day, producing a range of high-value-added petrochemical products and fuels. This capacity puts it on par with some of the world's leading petroleum processing facilities, such as the Jamnagar refinery in India. The construction of such a massive complex has brought together a workforce of thousands, peaking at over 70,000 workers during its most intense phases. These workers come from all over the world, bringing diverse skills to a project that requires precision engineering and sophisticated technology. One of the most significant challenges faced during the construction was the environmental management, given the sensitive marine and coastal ecosystems surrounding the site. The project employs advanced environmental technologies and systems to minimize ecological disruption, including water recycling processes and air quality control systems. Special features of the project include its state-of-the-art deep water terminal, which can accommodate very large crude carriers that transport crude oil across the globe. For our next project, we have to step into the bustling heart of British Columbia, where the Vancouver International Airport expansion is located. Launched in 2017, this expansive project was completed in 2022 with a cost of around 9.1 billion Canadian dollars. It's designed to accommodate the soaring passenger numbers, which are expected to reach 25 million annually by the end of the decade. This scale of growth brings its set of challenges and innovations, making the airport a focal point of Canadian aviation development. One of the most intriguing aspects of the expansion is the addition of a new international terminal wing. Spanning the length of nearly 3 Canadian football fields, the new wing is being built to handle the largest aircraft in the world. With 8 new gates, this terminal is not just large, but also a marvel of sustainability, designed to meet LEED Gold standards. The project also includes a massive upgrade to the airport's baggage handling system, increasing its capacity by 75%. This system will integrate cutting-edge technology to speed up baggage processing and improve the overall passenger experience. Construction at an operational airport presents the unique challenge of maintaining daily operations while minimizing disruption to passengers. The team has navigated these challenges through meticulous planning and phased construction, allowing the airport to remain fully functional as a key international hub. Comparatively, the scale of the airport's expansion is akin to adding a whole new airport the size of London City Airport right within its existing footprint. It's time to investigate the LNG Canada project next, which is a venture set to transform not only the landscape, but also the energy dynamics of the region. Initiated with a vision to tap into Canada's vast reserves of natural gas, the LNG project commenced in 2018 with an anticipated operational start by 2020. The project's grand scale is reflected in its $40 billion budget, making it the largest private sector investment in Canadian history. The ambition here is to liquefy natural gas efficiently and transport it across the globe, positioning Canada as a key player in the global energy market. The construction site itself spans over 400 hectares, equivalent to around 560 soccer fields combined. At the heart of the project are the advanced facilities designed to liquefy natural gas by cooling it to -162 degrees Celsius, transforming it into a liquid to reduce its volume nearly 600 times, making it easier and safer to store and ship overseas. The project's construction team employs cutting-edge construction techniques, including modular construction where large components are prefabricated elsewhere and assembled on-site, reducing construction time and environmental impact. The project is designed to achieve the lowest carbon intensity of any large-scale LNG plant in the world, utilizing renewable hydroelectric power for some of its processes, a significant departure from the more common reliance on fossil fuels for such operations. Challenges have been plentiful, ranging from logistical issues in transporting massive equipment through rugged terrain to navigating stringent environmental regulations that govern the preservation of the pristine northern British Columbia environment.
Chicago's position as a global transportation hub is being reinforced through one of the largest aviation infrastructure programs ever undertaken in the United States: the long-term modernization of O'Hare International Airport. This mega project stands as a central pillar among Chicago's largest construction efforts, reshaping air travel capacity, terminal design, and airfield performance for decades to come. The current modernization effort builds on earlier construction phases that began in the mid-2000s. The foundational work was the O'Hare Modernization Program, initiated in 2005, which focused almost entirely on the airfield itself. Prior to this program, O'Hare relied on intersecting runways that caused cascading delays during bad weather. Over a 16-year construction period, the airport added 4 new runways, extended 2 existing ones, and permanently closed several older runways. This reconfiguration created a parallel runway system, increasing hourly aircraft capacity and reducing delays by tens of thousands of flights annually. The final runway opened in late 2020, marking the operational completion of that phase by 2021. With the airfield rebuilt, Chicago shifted focus to the terminal complex through a new initiative known as O'Hare 21. This phase represents the most visible portion of the mega project and is currently underway. At the center of O'Hare 21 is the O'Hare Global Terminal, a new international terminal replacing the existing Terminal 2. Construction planning began in the late 2010s, with early site work and enabling projects starting in the early 2020s. Full-scale construction is expected to progress throughout the decade, with the terminal targeted for completion around 2030. The global terminal will fundamentally change passenger flow at O'Hare. It is designed to consolidate domestic and international arrivals in one location, eliminating the need for long transfers between terminals. The building will span more than 2 million square feet and include expanded customs processing, upgraded security screening, and redesigned concourses built to handle larger wide-body aircraft. Terminal 2 will be demolished in phases as the new structure is completed, allowing airport operations to continue throughout construction. Beyond the main terminal, the modernization includes 2 new satellite concourses located west of the existing terminal core. These concourses are critical capacity expansions and are being built in parallel with the global terminal. Satellite 1 is further along in planning and early construction, with utility relocation, foundation preparation, and tunnel alignments already established. Satellite 2 is scheduled for later phases, dependent on airline demand growth. Both satellites will be connected to the main terminal via underground pedestrian tunnels and an automated people mover system. Together, they are expected to add dozens of new gates, many capable of handling international flights. Supporting infrastructure is a major part of the mega project. New baggage handling systems are being installed to support higher passenger volumes and reduce transfer times between flights. Electrical substations, stormwater systems, and communications infrastructure are being upgraded or rebuilt to meet modern performance and resilience standards. These elements are largely invisible to passengers, but represent a substantial portion of construction cost and complexity. The project timeline extends into the early 2030s. While individual components, like satellite concourses, may open earlier, the full terminal area plan is expected to be substantially complete around 2032. Construction sequencing is designed to avoid disrupting daily operations at one of the busiest airports in the world, requiring extensive temporary facilities and phased demolition.
There are airports that simply connect cities. And then there's Denver International, an airport that feels more like a myth, wrapped in fog, conspiracy, and raw, undeniable scale. Set against the jagged silhouette of the Colorado Rockies, DN isn't just an air hub, it's a riddle in concrete, steel, and prairie wind. From the moment you approach, you realize this place is different. The terminal roof rises like a row of white peaks, a canvas of fabric stretched into spires that mimic the mountains beyond. It's both architectural poetry and functional design, a nod to the natural world in the middle of a high-tech frontier. But behind the beauty lies a beast of logistics and ambition. Denver International is the second largest airport in the world by land area. Spanning over 50 square miles, it's larger than Manhattan. That space isn't just empty fields, it's a calculated investment in the future. Room to grow. Room to reimagine what an airport can be. When DEN opened in 1995, it did so after delays, budget overruns, and more than a little controversy. It replaced the old Stapleton Airport, not because Denver needed a slightly better facility, but because it needed to think bigger, radically bigger. At the time, few could have predicted how essential that gamble would become. Today, with air traffic climbing and cities swelling, that oversized footprint now looks like foresight. Operationally, it's a marvel. The runways, 6 in total, are set wide apart, allowing simultaneous takeoffs and landings in nearly any weather. This efficiency is crucial in Denver's unpredictable climate, where snowstorms can whip in with little warning. Beneath the surface, a vast tunnel system once built for an ambitious, but famously flawed, automated baggage system still snakes its way below ground. A reminder of how pushing boundaries doesn't always go smoothly. Yet what truly sets Denver apart isn't just the infrastructure, it's the atmosphere. This airport breathes mystery. From strange murals to the giant blue horse sculpture at the entrance, complete with glowing red eyes, Den has become a magnet for conspiracy theories and urban legends. Secret bunkers, underground facilities, coded art. It's all part of the lore. Whether you believe any of it or not, there's no denying the airport has a presence. But look past the shadows, and you'll see something else. A living symbol of Denver's evolution. The airport isn't just a pit stop between coasts. It's a launchpad into the American West. It connects the Rockies to the world, fuels the city's economic engine, and anchors Colorado's global reach. And it does all of that with an eye on what comes next. Den is currently in the midst of multi-billion-dollar expansions, new gates, modernized terminals, and advanced security systems. It's shedding some of its 90s skin and stepping boldly into the 21st century. But even as it transforms, that original ambition, that sense of scale and audacity, still lingers in the wide-open airfields and endless walkways. Brightline West isn't an idea, it's under construction. A $12 billion high-speed rail megaproject designed to link Los Angeles to Las Vegas in just over 2 hours, cutting a trip that often takes over 5 by car. With speeds reaching 200 miles per hour and over 260 miles of new rail corridor, this is one of the largest and most complex infrastructure projects ever attempted in the American Southwest. The alignment runs primarily along the I-15 corridor, chosen for its straight path, existing right-of-way, and the massive volume of traffic it sees. Over 50 million people travel between LA and Las Vegas each year, many of them stuck in stop-and-go congestion. Building next to a major interstate, however, comes with logistical and engineering demands on a different scale. Crews must work within narrow margins between freeway traffic and construction zones, requiring extensive concrete barriers, temporary detours, and phased sequencing to avoid bottlenecks. The trains will operate entirely on dedicated, grade-separated track. That means no level crossings, no signal delays, and no sharing with freight or commuter rail, making Brightline West a true high-speed rail system by global standards. To achieve this, over 300 structures are being constructed along the route, including overpasses, bridges, wildlife crossings, and viaducts. Every one of them is engineered to withstand extreme desert heat, high wind speeds, and seismic loads consistent with California building codes. One of the most technically demanding sections involves crossing the Kaijon Pass, an elevation climb of over 3,000 feet between the Inland Empire and the high desert. This stretch requires extensive cut-and-fill operations, retaining walls and reinforced embankments. Specialized track design, including banked curves and controlled gradients, ensures that trains maintain high speeds without overstressing the vehicles or the infrastructure. Trackbed construction is another layer of complexity. Unlike conventional rail, high-speed systems require exacting tolerances for smoothness and alignment. The subgrade must be compacted and stabilized to millimeter-level accuracy, followed by multiple layers of ballast, reinforced concrete slab track, and vibration-damping materials. These systems are monitored in real time through embedded sensors, allowing for predictive maintenance and immediate response to deviations. Powering the system is an electrified catenary line running the full length of the corridor. This requires constructing hundreds of miles of new transmission infrastructure, including substations, overhead gantries, and high-voltage feeds. To ensure uninterrupted service, the power supply is designed with built-in redundancy and real-time switching capabilities. Utility coordination across 2 states and multiple counties adds further layers of complexity to every mile built. The train sets themselves, based on Siemens Velaro or similar European high-speed rail platforms, will be custom-modified for American standards. Each unit will feature aerodynamic nose cones, regenerative braking systems, crash energy management structures, and lightweight aluminum bodies to reduce axle load and track wear. These aren't commuter trains. They're precision-built machines designed to run at 200 mph across open terrain, with acceleration, deceleration, and safety systems modeled after Japan's Shinkansen and Germany's ICE.
Rather than rising from untouched land, the new Miami-Dade Airport emerged through one of the largest continuous airport reconstruction programs ever undertaken in the United States, transforming Miami International Airport into what is effectively a rebuilt megastructure operating in real time. Miami International Airport sits west of downtown Miami and functions as the primary global aviation gateway for South Florida and Latin America. By the late 1990s, the airport's original mid-20th century terminals, roadways, and airfield systems were no longer capable of handling projected passenger growth, new aircraft sizes, or modern security requirements. Miami-Dade County responded by launching a long-term capital improvement effort, commonly referred to as the airport's New Airport program, a reconstruction on the scale of a greenfield build while maintaining daily operations. The centerpiece of this transformation was the North Terminal Development Program, a multi-billion-dollar mega project that replaced large portions of the airport's aging infrastructure. Planning began in the late 1990s, with construction starting in the early 2000s. The program consolidated multiple older concourses into a single, linear terminal complex designed to improve passenger flow, security processing, and aircraft operations. Construction involved complete demolition of outdated concourses, utility corridors, and support buildings, followed by new foundations, structural frames, and terminal shells built adjacent to active runways and taxiways. This required phased construction sequencing to keep aircraft movements uninterrupted. New terminal structures were built using long-span steel and reinforced concrete systems capable of supporting large wide-body aircraft gates and high passenger volumes. The North Terminal was developed in multiple phases. Early phases focused on airside infrastructure, including new taxi lanes, aircraft parking aprons, and fuel hydrant systems. Subsequent phases delivered passenger processing spaces, including ticketing halls, security checkpoints, baggage handling systems, and customs facilities. The first major sections opened to passengers in the mid-2000s, with full substantial completion achieved in the early 2010s. A critical component of the new airport construction was the installation of an automated people mover system connecting the terminal to remote rental car facilities and parking structures. This required elevated guideways, stations integrated into terminal buildings, and control systems installed above active roadways. The people mover significantly reconfigured landside access to the airport. The reconstruction extended beyond terminals. Miami-Dade County invested heavily in runway rehabilitation and expansion, including pavement reconstruction, lighting upgrades, and drainage improvements. Taxiway geometry was modified to accommodate larger aircraft, such as the Airbus A380 and Boeing 777. These airfield works were completed incrementally over many years, often overnight, to avoid disrupting flight schedules. Cargo infrastructure was also rebuilt as part of the airport's Megaproject evolution. New cargo buildings, cold storage facilities, and access roads were constructed to support Miami's role as a major freight hub for perishable goods. These upgrades aligned with parallel megaprojects at Port Miami, reinforcing the county's logistics network. Security and resilience upgrades formed another major construction layer. Post-9/11 requirements led to reinforced terminal layouts, expanded security screening zones, and hardened building systems. Mechanical, electrical, and plumbing systems were replaced or upgraded to modern standards, including redundant power supplies and advanced fire protection. Flood mitigation and drainage improvements were incorporated to address Miami's climate and storm exposure. The timeline of the new Miami-Dade Airport build spans more than a decade. Major construction activity peaked between roughly 2004 and 2012, with continuous smaller projects extending beyond that period. By the early 2010s, the airport had effectively transitioned from a mid-century facility into a modern aviation megastructure, capable of handling tens of millions of passengers annually. Within the broader context of Miami's biggest megaprojects, the airport reconstruction stands alongside developments such as the Port of Miami Tunnel, Brickell City Center, and large-scale transit investments. Unlike vertical megaprojects, the airport rebuild was horizontal and systemic, requiring coordination across aviation operations, federal agencies, contractors, and airlines. If you've ever traveled through Britain by train, you know the experience can be both scenic and slow, with Victorian-era infrastructure still carrying millions of passengers every day. That's exactly what the HS2 project set out to change, a high-speed rail line designed to reshape how the country moves, connecting London with the Midlands and the North at speeds the UK has never seen before. It was imagined as the backbone of a new, modern transport network, one that could rival continental Europe's fast and efficient trains while easing the pressure on the country's crowded existing lines. High Speed 2, or HS2, is being built in stages. The first phase stretches from London to Birmingham, cutting travel times almost in half. The second was originally meant to continue north toward Manchester and Leeds, linking major cities with sleek new trains running at over 320 kilometers per hour. The ambition wasn't just about shaving minutes off journeys, it was about balancing Britain's economic geography, pulling growth and investment away from the capital and spreading it toward regions that had long been left behind. In theory, faster travel meant stronger regional economies, easier business connections, and new job opportunities across the country. But building HS2 has been anything but straightforward. It's one of the largest infrastructure projects in Europe, involving hundreds of kilometers of tunnels, viaducts, and embankments carved through some of England's most densely populated areas. The sheer complexity of the route required boring machines to tunnel under London suburbs, elevating tracks across countryside landscapes, and even designing specially built wildlife bridges to protect local ecosystems. Every section of the project is a microcosm of engineering challenges: soft clay, urban congestion, ancient infrastructure, and a constant balancing act between speed, safety, and sustainability. The construction workforce alone numbers in the tens of thousands, operating across dozens of sites at once. Giant tunnel boring machines, each named and tracked like ships, have been chewing their way through chalk and clay beneath the Chiltern Hills, creating vast underground passageways for the new line. Elsewhere, massive viaducts rise over river valleys, and new depots and stations take shape in cities that have been waiting decades for this kind of modernization. Euston and Old Oak Common in London are being transformed into vast transport hubs. designed not just for HS2, but to connect seamlessly with existing networks, integrating the old with the new. However, despite its technical brilliance, HS2 has faced intense criticism and political turmoil. Costs have soared far beyond initial estimates, delays have stacked up, and parts of the northern extensions have been scaled back or cancelled entirely, leading many to question whether the project can still deliver on its original promises. Environmental groups have voiced concerns about the loss of woodland and natural habitats, while others argue that the benefits to the broader economy still justify the disruption. Even so, what remains of HS2 still represents a massive leap forward for Britain's rail system. When the first trains begin running between London and Birmingham, they'll mark the country's entry into true high-speed travel, a mode that much of the world has already embraced. And while the vision may have shrunk from its earliest days, the project still stands as a symbol of long-term ambition, the kind of investment that tries to build not just for today's commuters, but for generations yet to come.
Few structures have ever emerged from the ground with such poetic symmetry and brutal precision as Beijing Daxing International Airport. Born from an urgent need to relieve pressure from the overcrowded Beijing Capital Airport, Daxing was never going to be just a supplement. It was designed from the start as a symbol of China's ascendancy in aviation, infrastructure, and high-speed construction. The plan was staggering. A brand new airport built from scratch in less than 5 years, capable of handling tens of millions of passengers annually, and anchored by one of the most architecturally complex terminal structures ever attempted. The site chosen was flat and unremarkable farmland in the Daxing district, but it was about to become the nucleus of a new economic corridor. Before a single column could rise, thousands of workers, engineers, and machines had to transform an empty stretch of land into one of the most interconnected transportation hubs on Earth. At the heart of the project was the terminal itself, a sweeping, starfish-like structure that pushed the boundaries of spatial design. The challenge wasn't just to make it beautiful, but to make it brutally efficient. A central node with 6 extending arms meant that all gates could be reached with a maximum walking distance of just a few hundred meters, radically improving passenger flow. But constructing such a layout meant tackling extreme technical complexity. The roof alone is an engineering spectacle, a vast, undulating canopy of steel and glass that required precision assembly down to the millimeter. Dozens of custom-fabricated joints, expansion mechanisms, and modular support systems had to be installed in perfect harmony to accommodate both structural loads and seasonal temperature swings. Massive steel trusses, each weighing dozens of tons, were hoisted into place in synchronized operations that resembled the choreography of a space mission more than a traditional building site. Underground, an entirely separate world was being constructed. Beneath the terminal, construction crews carved out a multi-level labyrinth of tunnels, utility corridors, and high-speed rail links, some of which were laid concurrently with the rising terminal structure above. Timing and sequencing were everything. Sections of the underground rail platforms had to be sealed and reinforced, even as excavations were still ongoing elsewhere. The integration of subway lines, intercity trains, and future maglev systems meant that crews were building not just for today's capacity, but for a future where the airport would sit at the heart of a mega-regional transport network. Every slab of concrete, every steel beam underground had to be laid with total synchronization with the structural demands above ground. And all of it had to happen without pause. Construction logistics on this scale verge on the surreal. Materials were delivered with military precision, steel from multiple provinces, glass from high-performance manufacturers, and prefabricated components trucked in across thousands of kilometers. On-site coordination was controlled through centralized digital platforms, utilizing BIM, Building Information Modeling, to track every component, system, and timeline in real time. Massive cranes, custom-built for the height and reach required, moved like slow, mechanical dancers across the worksite, while armies of workers labored beneath them in shifts that rarely stopped. The workforce was huge, tens of thousands at the peak of construction. Yet safety records remained among the best in the region due to a combination of strict protocols and smart monitoring systems. Environmental considerations, too, were built directly into the construction process. Entire stormwater retention systems, solar panel arrays, and thermal insulation technologies were integrated from the beginning, not tacked on as afterthoughts. The runways, of which multiple were built in parallel, were laid with advanced materials designed to withstand decades of use and extreme weather conditions. Drainage systems were buried deep and wide, designed to handle Beijing's summer rains without compromising operations. Fuel systems, baggage conveyors, HVAC installations, all were constructed with a mind toward redundancy, modularity, and long-term resilience. In the heart of the Arabian Desert, where sand stretches endlessly toward the horizon, there lies an airport so vast it could swallow entire cities. King Fahd International Airport, just outside Dammam, Saudi Arabia, isn't merely a transportation hub. It's a monument to scale, ambition, and the futuristic vision of a kingdom that dared to build big. At over 780 square kilometers, the airport's property makes it the largest in the world by land area. That's not a typo. It's larger than the entire country of Bahrain. But what makes King Fahd International truly extraordinary isn't just its size. It's the statement it makes, that Saudi Arabia isn't content to follow the pace of global infrastructure. It intends to set it. Opened to commercial traffic in the late 1990s, this megastructure was designed not only to serve the growing eastern province, but also to position the kingdom as a logistical and geopolitical crossroads. Dammam, with its proximity to the Persian Gulf and to vital oil installations, was the perfect place for such a venture. And this airport, carved out of the desert like a futuristic fortress, was built to handle millions of passengers a year, with room to grow even further. But numbers only tell part of the story. The architecture speaks volumes too. From its mosque, one of the most serene and striking features of the complex, to its sweeping terminal design, every part of the airport reflects a blend of modern engineering and cultural reverence. The main terminal, with its clean lines and monumental scale, is a physical metaphor for Saudi Arabia's pivot to the future while staying rooted in heritage. The sheer logistics of managing an airport spread across hundreds of square kilometers is a feat of engineering unto itself. Road networks, utility corridors, and support facilities stretch like a web over the arid landscape. Even with only a portion of the total land developed, the airport manages to operate efficiently, thanks to meticulous planning and cutting-edge control systems. Beyond the infrastructure lies the human element, the workers, planners, and engineers who've kept this mammoth operation running for decades in one of the most challenging climates on Earth. Heat, sand, and isolation have tested every part of this project, yet it remains a key artery for both domestic and international travel. As Saudi Arabia charts a new course under its Vision 2030 plan, aiming to diversify its economy and become a global hub for business and tourism, King Fahd International is poised to play an even larger role. With capacity upgrades, potential expansions, and its proximity to future smart cities, this desert giant is far from finished. Jordan Downs wasn't built to last, but it lasted. What began in the 1940s as temporary war worker housing in the heart of Watts evolved into one of Los Angeles's most recognized public housing projects. For decades, it stood as a symbol of neglect, of disinvestment, of the city's fractured promises. Now it's at the center of one of the largest and most complex urban redevelopments ever attempted in Southern California. This is the Jordan Downs redevelopment, a multi-phase billion-dollar megaproject that's rebuilding an entire neighborhood from the ground up. We're not talking about a simple renovation. This is full-scale urban reconstruction, replacing over 700 aging public housing units with a mixed-income community of more than 1,400 new homes, complete with parks, retail corridors, a new street grid, and state-of-the-art infrastructure. And all of it is happening while people still live there. That reality, redeveloping a live-in community without displacement, is what makes this project such a massive logistical and engineering challenge. Everything had to be phased. Crews couldn't just level the site and start fresh. Instead, new housing blocks were constructed in stages on available land, allowing families to relocate within the community as old units came down. That required intense coordination, not just in construction, but in utilities, access roads, and safety systems, all while keeping the neighborhood functioning. Before any new buildings could rise, the land itself had to be re-engineered. Jordan Downs sits on a former industrial site, contaminated from decades of adjacent manufacturing. That meant full environmental remediation, soil testing, removal of hazardous material, groundwater management, and installation of protective barriers. Engineers excavated tens of thousands of cubic yards of earth, replacing contaminated soil with engineered fill, compacted and monitored for stability. Next came infrastructure. The original Jordan Downs layout was a relic of mid-century planning. Isolated blocks with limited connectivity and almost no integration into the surrounding street grid. To fix that, the project involved installing an entirely new road network, complete with sidewalks, bike lanes, storm drains, and underground utilities. A major extension of Century Boulevard now runs through the site, connecting it to the broader Watts area and giving the community a direct arterial link to the rest of the city. Structurally, the new buildings are designed for both density and resilience. Wood frame over concrete podiums dominate the design, balancing cost efficiency with seismic durability. Each structure is engineered with fire suppression systems, earthquake-resistant framing, and energy-efficient insulation to meet California's Title 24 building codes. Sustainability was also baked in. Solar panels, drought-tolerant landscaping, and stormwater capture systems are integrated across the site. And unlike the original layout, the new Jordan Downs is being built with mixed-use development at its core. A central retail village is part of the plan, complete with grocery stores, cafes, and community-serving businesses. That required additional engineering for load-bearing slabs, commercial-grade ventilation, and enhanced utility access to support food service and retail operations. The project also includes new parkland, recreational facilities, and space for schools and job training centers, all of which had to be laid out on what was once a closed, fenced-off grid.
Lincoln Yards was approved as a planned development by the City of Chicago in 2019. The approval framework allows for up to approximately 14 million square feet of total development, making it one of the largest private real estate projects ever approved in the city. The master plan includes high-rise residential towers, office buildings, life sciences facilities, retail space, hotels, and cultural venues, with development spread across multiple phases projected to span more than a decade. A critical component of the project is its infrastructure construction, much of which must be completed before vertical development can occur. Planned infrastructure work includes new internal road networks, utility corridors, riverwalk expansions, and flood mitigation systems. One of the most significant infrastructure elements is the proposed extension and redesign of arterial roadways to connect the site more effectively to surrounding neighborhoods and regional transportation networks. Transit has been a central planning issue for Lincoln Yards. The original approval included provisions for a new CTA rail station on the Red Line, intended to support future density. While the station is not yet funded or scheduled for construction, planning and right-of-way considerations were integrated into the site layout. Interim transportation strategies rely on bus service enhancements, bike infrastructure, and pedestrian connections. Vertical construction was initially anticipated to begin in the early 2020s, with early phase buildings focused on office and life sciences users near the river. However, shifting market conditions, financing challenges, and changes in office demand delayed large-scale building starts. As a result, much of the project remains in a pre-vertical construction phase, with focus placed on land preparation and long-term infrastructure planning rather than skyline-defining structures. Environmental and flood resilience construction plays a major role in the project's scope. Portions of the site lie within a floodplain, requiring elevated building pads, stormwater detention systems, and reinforced river edges. These systems are designed to meet modern floodplain management standards and reduce pressure on Chicago's combined sewer system. The full build-out timeline for Lincoln Yards has always been long-term. Even under original projections, completion was expected to occur in phases extending into the 2030s. Current expectations continue to place full development well into the next decade, with construction activity expected to ramp up incrementally rather than all at once. This phased approach allows the project to adapt to economic conditions while maintaining entitlement approvals. In the broader context of Chicago's megaprojects, Lincoln Yards differs from infrastructure-driven efforts like airport expansions or flood control systems. Its scale comes from land area, development rights, and long-term transformation rather than a single signature structure. If completed as approved, it would introduce tens of thousands of residents and workers to a formerly industrial zone, reshaping the North Branch corridor.
Not every airport begins with a blank slate. Some rise out of the chaos of overburdened infrastructure, and others, like Shanghai Pudong International, are built with foresight, planned from the ground up to handle a future that had not yet arrived. In the 1990s, Shanghai's existing airport, Hanhikivi, was bursting at the seams, hemmed in by the city's explosive growth. The answer wasn't to expand within, it was to build outward, toward the coast. What followed was a high-speed campaign to reclaim land from the East China Sea and erect one of the most strategically engineered air hubs in Asia. Construction began not on solid land, but on soft, low-lying tidal flats. These coastal mudlands presented a serious engineering challenge. To establish a stable foundation, workers undertook an enormous land reclamation effort. Millions of cubic meters of sand and earth were dredged, compacted, and layered to form a platform strong enough to carry the weight of runways, terminals, and supporting structures. To prevent long-term subsidence, a real threat in such terrain, engineers employed deep piling techniques and advanced geotextile stabilization systems. It wasn't just about laying the groundwork. It was about making sure that groundwork could last for decades under the pressure of non-stop air traffic. Once the land was stabilized, Pudong's first phase was fast-tracked into reality. The master plan was modular and scalable, with future expansion built into the DNA of the project. Terminal 1, with its long, linear design, was constructed to handle the rising wave of international traffic, linking China's financial hub with the global economy. The roof structure, supported by a forest of sleek steel columns, was engineered for both visual lightness and structural strength, while large spans of glass maximized daylight without sacrificing thermal performance. Inside the terminal's shell, kilometers of electrical, plumbing, fire protection, and air handling systems had to be embedded with flawless precision. Every conduit and junction coordinated across dozens of contractors and engineering teams working simultaneously. The initial runway system was laid with equal attention to durability and volume. High-performance concrete was poured in long, uninterrupted sessions to create seamless surfaces for large-bodied aircraft. Drainage systems had to be designed not only for heavy rainfall, common in the region, but also for the complex water table beneath the reclaimed land. Pump stations, culverts, and storm channels were embedded into the very bones of the airport to ensure operations could continue during typhoons or seasonal flooding. Every phase was built with layers of redundancy, reflecting an understanding that resilience wasn't optional, it was foundational. As Shanghai's international profile soared, so did the scale of Pudong's ambitions. Terminal 2 was added in a massive expansion that more than doubled capacity, echoing the architectural language of the first terminal while integrating newer materials and systems. This phase included another runway, part of a broader plan to maintain aircraft flow without bottlenecks, and an underground transit network linking terminals and remote facilities. Construction crews worked in tandem with aviation authorities to ensure that all additions complied with evolving international standards, from runway safety zones to advanced baggage screening systems. The most striking construction achievement in later phases was the satellite concourse system. Gigantic structures linked by underground automated people movers. These satellite buildings weren't just appended, they were engineered to function as high-capacity extensions of the terminals, with full customs, immigration, and boarding infrastructure integrated underground and vertically. Building these while the airport remained fully operational required phased rollouts, nighttime shifts, and relentless coordination to avoid disrupting flight schedules. Olympic Plus Hill isn't subtle. At 760 feet tall, it's one of the tallest residential towers ever built in Los Angeles. An enormous vertical structure that carves its presence directly into the downtown skyline. Located at the crossroads of Olympic Boulevard and Hill Street, this project is pure scale. Over 800 residential units, 60 stories, and more than 1 million square feet of combined residential, retail, and amenity space. But the story here isn't just size. It's how engineers managed to build something this massive in the seismic heart of California. The foundation work alone pushed limits. To support the weight of the tower, deep piles had to be drilled through layers of soft fill and clay until reaching bedrock, some driven more than 80 feet into the ground. The base isn't just strong, it's smart. A reinforced concrete core, wrapped in steel and designed with shear walls, creates a seismic-resistant spine capable of swaying without breaking. That's essential in a city where ground movement isn't a possibility. It's an inevitability. Once the base was in place, construction moved upward at a rapid pace. Crews used self-climbing formwork systems that latch onto the tower's core, lifting themselves with each pour of concrete. Every floor was built in a tight cycle. Pour, cure, lift, repeat, often turning around a new floor in under 5 days. Each level had to align perfectly, not just vertically, but in terms of internal systems. Plumbing, electrical, fireproofing, and post-tensioning cables all had to be laid out with centimeter-level precision. The tower's skin, a curtain wall system made of high-performance glass and aluminum, presented its own set of challenges. At 60 stories, installing massive panels of glass isn't just dangerous, it's a logistical problem. Wind conditions shift rapidly at height, and each panel had to be lifted by crane and installed within narrow time windows to avoid delays. The glass isn't just aesthetic, it's engineered for insulation, glare reduction, and earthquake flexibility, with anchor points that allow for controlled movement. Olympic Plus Hill also demanded an advanced vertical transportation system. With so many units stacked vertically, elevator wait times could have crippled usability. To solve that, engineers installed high-speed traction elevators managed by a destination dispatch system, software that assigns elevators based on passengers' final destinations rather than button presses. It reduces stops, speeds up trips, and keeps the tower moving efficiently even at peak times. Parking and access were another challenge. With limited surface area and thousands of potential residents and visitors, a multi-level underground parking structure was integrated into the base, complete with car stackers and electric vehicle charging systems. Coordinating excavation and support for that structure, while still maintaining the structural integrity of surrounding streets, required careful sequencing and real-time monitoring of ground pressure and movement.
Rising from the western edge of downtown Miami, Panorama Tower represents one of the most consequential vertical construction efforts in the city's modern history and stands as a defining chapter in Miami's era of megaproject development. Panorama Tower is an 85-story, mixed-use skyscraper located at 1101 Brickell Avenue, positioned at the intersection of Brickell Downtown and the Miami Health District. When it topped out, it became the tallest building in Florida, reaching a structural height of approximately 868 feet. Construction began in 2013, and the tower was officially completed in 2018, following a multi-year development cycle that coincided with Miami's rapid transformation into a global, high-rise city. The project was developed by Florida East Coast Realty, a company with deep historical ties to the state's infrastructure and urban development. Panorama Tower was conceived not as a single-purpose building, but as a vertically integrated megastructure combining residential, office, hotel, and retail space within one footprint. This approach reflected a broader shift in Miami construction during the 2010s, where land constraints and economic growth pushed developers toward dense, mixed-use, vertical solutions. The construction scope of Panorama Tower was extensive and technically demanding. The tower contains more than 2.8 million square feet of total built area. Its program includes approximately 821 residential units, over 200,000 square feet of Class A office space, a 208-room hotel, and significant ground-level retail and parking infrastructure. The building's foundation required deep piling systems designed to anchor the structure into Miami's limestone bedrock, a critical engineering challenge given the city's high water table and coastal soil conditions. Structurally, Panorama Tower uses a reinforced concrete core and shear wall system, a method commonly employed in super tall residential towers, but executed here at unprecedented scale for Florida. High-strength concrete mixers were required to handle vertical loads at extreme heights, and the construction sequence demanded precise coordination to maintain schedule while pouring floor plates at increasing elevations. Wind engineering played a central role in the design, with the tower engineered to withstand hurricane-force wind loads common to South Florida. Construction logistics were particularly complex due to the site's proximity to major roadways and active urban districts. Crane operations, concrete deliveries, and vertical material transport had to be tightly managed to minimize disruption to surrounding neighborhoods. At peak construction, hundreds of workers were on site daily, contributing to one of the largest active construction projects in Miami at the time. The timeline of Panorama Tower closely mirrors Miami's broader construction boom. Groundwork and foundation activities began shortly after the 2013 groundbreaking. Vertical construction accelerated between 2015 and 2017, during which the tower surpassed all other buildings in the state in height. Topping out occurred in late 2017, marking a symbolic milestone for Miami's skyline. Interior build-out, systems commissioning, and phased occupancy continued into 2018, when the project reached full completion. Within the context of Miami's megaproject landscape, Panorama Tower stands alongside developments such as Brickell City Center, Miami World Center, and the ongoing expansion of the downtown and Brickell corridors. Unlike large multi-block projects, Panorama Tower condensed megaproject scale into a single vertical structure, demonstrating how Miami's growth could be achieved upward rather than outward. The building also marked a shift in how Miami approached mixed-use density. By stacking residential, hospitality, and commercial uses, Panorama Tower reduced reliance on horizontal sprawl and car-dependent layouts. Its parking systems, mechanical floors, and vertical circulation were engineered to support thousands of daily occupants within a single building envelope. South of McCormick Place, and stretching toward the edge of Lake Michigan, one of Chicago's largest proposed redevelopment megaprojects is planned on land long isolated from surrounding neighborhoods. The Bronzeville Lakefront project is a multi-phase, mixed-use development centered on the former Michael Reese Hospital site, representing a major attempt to reconnect Bronzeville to the lakefront through large-scale construction and infrastructure investment. The project area encompasses roughly 48 acres, bounded by 31st Street, 43rd Street, Lakeshore Drive, and the Metra Electric Rail Corridor. For decades, the site was dominated by the Michael Reese Hospital campus, which was demolished in the early 2010s following the city's unsuccessful bid for the 2016 Olympic Games. Demolition and site clearance marked the first major construction phase, removing dozens of buildings and leaving one of the largest undeveloped parcels on Chicago's lakefront. After demolition, the land remained largely vacant while planning efforts evolved. The Bronzeville Lakefront vision emerged as a long-term redevelopment framework rather than an immediate construction project. The master plan proposes millions of square feet of new development, including residential buildings, office and research space, institutional facilities, hotels, and retail. The scale places it firmly among the most ambitious mega projects proposed on Chicago's South Side. Infrastructure construction is central to the project's feasibility. The site requires new internal street grids, utility systems, and stormwater management infrastructure before vertical construction can occur. Because the land sits near the lake and adjacent to major transportation corridors, flood resilience and drainage engineering are critical components. Planned construction includes elevated building pads and modern stormwater detention systems designed to reduce runoff into Lake Michigan. One of the most significant proposed elements is a life sciences and innovation campus intended to anchor early development phases. This component would include laboratory buildings, research facilities, and office space designed to attract medical and biotech institutions. These buildings are expected to be among the first vertical structures constructed once infrastructure work advances, establishing employment density before residential build-out accelerates. Residential construction is planned to follow in multiple phases. The master plan allows for thousands of housing units, including a mix of market rate and affordable housing. Buildings are expected to range from mid-rise to high-rise, with height transitions designed to integrate with surrounding Bronzeville neighborhoods. Construction sequencing is intended to spread residential delivery over many years to match demand and financing availability. Transportation access is a major planning driver. The site is adjacent to Lakeshore Drive and served by the Metro Electric Line, with future improvements expected to enhance station access and pedestrian connectivity. Proposed construction includes new pedestrian bridges, improved crossings, and internal bike and transit infrastructure to reduce reliance on cars and better integrate the development with nearby communities. Unlike many downtown megaprojects, Bronzeville Lakefront places heavy emphasis on public space construction. Plans include new parks, plazas, and lakefront connections intended to extend recreational access southward. These spaces are expected to be built incrementally alongside private development, requiring coordination between public agencies and private developers. Timeline projections for Bronzeville Lakefront extend well into the 2030s. Early infrastructure and anchor projects are expected to define the first major construction phase, followed by successive waves of vertical development. Full build-out has always been envisioned as a multi-decade effort rather than a single construction cycle, reflecting both the size of the site and the complexity of funding and approvals. Tucked away in the mountains of Guizhou province in southwestern China, there's a gorge so deep and narrow that sunlight barely reaches the river at the bottom for most of the day. And spanning this massive cut in the earth, high above the mist and cliffs, engineers are building something that almost defies belief: the Huajiang Grand Canyon Bridge. When complete, it will stand among the highest bridges ever built on the planet. A structure so tall that if you dropped a skyscraper from the deck, it would fall for seconds before touching the valley floor. The numbers behind it are staggering. The bridge deck will rise over 600 meters above the river, which means it's taller than most observation towers and higher than the top floor of the Shanghai Tower. To put that in perspective, imagine stacking 2 Eiffel Towers end to end. That's roughly the drop from the roadway to the canyon below. This kind of height doesn't just make for dramatic photos, it turns every stage of construction into a feat of courage and precision. Workers spend their days suspended hundreds of meters in the air, guiding steel cables, assembling segments, and balancing heavy machinery on platforms that hang in the clouds. The Huajiang Grand Canyon Bridge is part of a new expressway that will connect cities across Guizhou, one of China's most mountainous provinces. Historically, this region was isolated by its terrain, deep valleys, twisting ridges, and karst formations that make road building incredibly difficult. The bridge is designed to close one of the biggest gaps, cutting travel times from hours to minutes, and linking communities that once felt worlds apart. In a province known for its poverty and difficult logistics, projects like this aren't just about transport, they're about access, trade, and opportunity. Structurally, it's a suspension bridge, chosen because it's one of the few designs that can handle both the span and the height of the canyon. The main span stretches more than 1 kilometer across, supported by enormous cables that anchor into the mountains on each side. The anchorages alone are buried deep in concrete and rock, absorbing the colossal tension forces that hold the deck steady. Every component must withstand fierce winds, extreme temperature shifts, and the constant pull of gravity across an open void. Even the construction of the towers is an achievement, with cranes and scaffolding perched on cliffs that would make most people's legs shake just looking down. What makes the Huajiang project even more impressive is how it reflects China's relentless drive to conquer geography with infrastructure. Guizhou has become a global showcase for bridge engineering, home to more of the world's highest bridges than any other region. Each one seems to push the limits a bit further. Higher decks, longer spans, faster timelines. The Huajiang Bridge is simply the next leap in that sequence, proving that there's almost no terrain too challenging to cross. When it finally opens to traffic, drivers will glide across a stretch of road that looks like it's floating between mountains, with clouds drifting below and the canyon yawning far beneath. It's one of those places where engineering and nature meet in a way that's both awe-inspiring and humbling, a reminder of what human ingenuity can achieve when the landscape dares us to go higher.
Some airports evolve slowly, layer by layer, molded by decades of growth. George Bush Intercontinental Airport in Houston, however, was born with a blueprint for scale from the very beginning. Constructed in the late 1960s to relieve pressure on the aging William P. Hobby Airport, IAH was never intended to be a simple regional terminal. It was a forward-looking investment, a modern answer to the booming oil economy and Houston's ascent as a global city. The site selected was expansive, a heavily forested stretch of North Houston that offered the space needed to dream big. Clearing the land was a massive undertaking on its own, requiring the removal of dense vegetation, rerouting of creeks and water flows, and the construction of entirely new utility corridors before the first runway could even be considered. Once the land was prepped, construction began with an ambitious but calculated layout. Instead of a single terminal, the airport would use a decentralized multi-terminal model, with each terminal functioning semi-independently while connected via road and eventually underground train. This modular design was intended to accommodate rapid expansion without crippling the core infrastructure. Each terminal could grow, be retrofitted, or replaced without overhauling the entire system. Early construction focused on 3 primary terminals, A, B, and C, each rising in parallel over poured concrete foundations and skeletal steel frameworks. The terminal buildings themselves were constructed with long-span trusses, allowing for wide, open concourses that minimized interior columns and maximized flexibility for airline operations. As the airport expanded, so too did its runways, crafted to handle the full spectrum of aircraft, including wide-body international jets and high-volume domestic carriers. Runway construction required extensive excavation and grading work to create a perfectly level base in Houston's famously unstable clay-heavy soil. Crews implemented multi-layered sub-base systems, including geotextile membranes, to prevent cracking and heaving from the area's intense rainfall and temperature swings. Parallel runways were spaced widely enough to allow simultaneous takeoffs and landings, an operational advantage critical to IAH's future role as a hub. Throughout the 1980s and 1990s, construction never truly stopped. Terminal C was expanded into a major domestic hub for Continental Airlines, and later, Terminal E was constructed as an international gateway. The development of Terminal E marked a shift toward high-capacity, high-efficiency construction. It featured dual-level road access, streamlined customs and immigration facilities, and modern jet bridges designed for next-generation aircraft. The supporting infrastructure was just as critical. New parking structures, maintenance facilities, and de-icing pads were all built to support the increasing traffic load. Simultaneously, the airfield lighting, navigational aids, and fueling systems underwent modernization to comply with FAA regulations and future-proof the site. Beneath the terminals, the construction of the airport's people mover system added a layer of subterranean complexity. Engineers bored deep into Houston's wet subsoil to install guideways and tunnels for the train, requiring continuous dewatering, careful slope stabilization, and waterproofing membranes to prevent long-term seepage and erosion. The result was a fully automated train system that allowed passengers to move between terminals without surface traffic interference, an operational necessity in an airport spread across thousands of acres. Every phase of expansion at IOH has demanded not just engineering expertise, but logistical acumen. The airport had to remain operational throughout each construction phase, meaning crews often worked overnight or in carefully isolated zones to avoid disrupting flight schedules. Coordinating contractors, security, utilities, and aviation authorities required a master-level orchestration of timelines and contingency planning. Yet through each stage, whether laying runway concrete under humid Gulf skies or welding steel at height, Houston's flagship airport grew into a true international gateway, one poured and riveted together by sheer logistical ambition. The G Line, formerly known as the Orange Line, was never designed to stay the same. From the beginning, it was a workaround, a bus rapid transit route built in place of a rail line due to funding constraints and political compromise. But over time, its ridership and strategic location forced the city to rethink what it could be. Now the G Line is undergoing a major transformation, an infrastructure upgrade project spanning the entire 18-mile corridor through the San Fernando Valley, pushing the limits of what bus transit can do in Los Angeles. The goal is simple: increase speed, capacity, and safety. But executing that goal has required deep and complex engineering interventions at nearly every point along the route. One of the most critical changes is the installation of a state-of-the-art signal priority and preemption system. Unlike traditional traffic signals that respond to fixed timers or limited sensors, this system actively clears intersections ahead of approaching buses, reducing delays and allowing for smoother flow across dozens of street crossings. Another major element is the construction of grade separations, rail-style overpasses and underpasses, at the busiest and most delay-prone intersections. Key locations like Sepulveda Boulevard, Van Nuys, and others are being excavated and rebuilt with concrete bridges and undercrossings to allow buses to pass through without ever stopping for cross-traffic. These structures require complex retaining wall systems, traffic rerouting, and in some cases, full reconstruction of local street infrastructure around the new grades. To support higher frequency service, the corridor is being outfitted with new power systems, bus-only lanes resurfaced with heavy-duty concrete, capable of supporting constant vehicle weight, and upgraded station platforms. The existing asphalt guideway, originally built to mimic light rail tracks in layout, has been deteriorating under the strain of articulated buses. Rebuilding it requires full-depth removal and replacement with reinforced concrete slabs, tied into a subsurface drainage system to prevent water intrusion and pavement shifting over time. Platform upgrades go beyond aesthetics. Stations are being lengthened to accommodate longer, higher-capacity buses and future electric models. Each platform is being raised and re-leveled to allow for near-zero gap boarding, speeding up passenger flow and improving accessibility. Integrated electrical conduits and utility vaults are also being installed during construction to prepare for future overhead charging systems as the fleet transitions to full electric. A core part of the upgrade involves upgrading the actual vehicle fleet. Metro is phasing in battery electric buses with larger passenger capacities, regenerative braking systems, and onboard diagnostics. These buses weigh more than their natural gas predecessors, which has direct implications for bridge loading, braking distances, and pavement wear. Engineers had to revisit structural tolerances across the entire corridor, from culverts and embankments to turning radii and clearance zones, to ensure long-term durability under heavier rolling stock. Fiber optic lines are also being laid alongside the corridor to support real-time monitoring. Everything from vehicle location, signal interaction, passenger load, and environmental data will be fed into Metro's central control center. This data will be used not just for dispatch, but but to dynamically adjust signal cycles and reroute in case of emergencies. Drainage systems along the G line were never built for current-day storms. As part of the upgrade, culverts are being expanded, bioswales are being added to medians, and runoff channels are being lined with concrete and fitted with sensors to monitor flow levels during heavy rain. All of this is necessary to prevent trackway flooding and preserve the subgrade from erosion.
Covering more than 27 acres across multiple downtown blocks, Miami World Center is not a single construction project, but a layered mega project built through coordinated phases that collectively reshaped the northern edge of downtown Miami. Miami World Center is located north of the Central Business District, bounded generally by Northeast 2nd Avenue, Interstate 395, and Northeast 8th Street. The site consisted for decades of underutilized parcels, surface parking, and fragmented low-rise structures. Formal planning for redevelopment began in the early 2000s, with land assembly occurring gradually over many years. The scale of the site required a master-planned approach rather than a single build execution. Major construction activity began in the mid-2010s, following zoning approvals and infrastructure agreements with the City of Miami and Miami-Dade County. Early phases focused on horizontal construction, including demolition, mass grading, utility relocation, and the installation of new underground infrastructure. Water, sewer, power, communications, and stormwater systems were rebuilt to support millions of square feet of future development. A defining construction element of Miami World Center was its internal street grid. New public streets were carved through the site, requiring roadway construction, drainage systems, sidewalks, lighting, and streetscape elements. These streets were designed to function as permanent city infrastructure rather than private access roads, integrating the development into the surrounding urban fabric. Vertical construction followed in multiple, overlapping phases. Residential towers were among the first major structures to rise, each requiring deep foundations suited to Miami's limestone geology and high groundwater conditions. Pile foundations, reinforced concrete cores, and high-rise flat-plate floor systems were used across most towers, with construction sequenced to allow simultaneous builds on adjacent parcels. Retail and commercial structures were developed at the podium and street levels. These buildings required large-span structural systems to create flexible interior layouts for tenants. Mechanical and electrical systems were distributed through shared service corridors to reduce redundancy across the district. Loading docks and service access points were consolidated to minimize street-level disruption. One of the most significant infrastructure integrations within Miami World Center was its relationship with regional transit. The development was designed around proximity to Brightline's Miami Central Station, as well as Metro Rail, Metro Mover, and bus connections. Pedestrian corridors and public spaces were constructed to funnel foot traffic between transit nodes and interior blocks, requiring careful grading and structural decking over below-grade utilities. Construction timelines varied by parcel. Early residential and retail components began delivering units around 2018 and 2019. Additional towers and commercial buildings were completed in the early 2020s, with construction continuing in phases as market conditions and financing allowed. Unlike a single mega project with a fixed end date, Miami World Center evolved through staggered completions. Hotel construction formed another major component. Large hospitality structures required distinct structural and mechanical systems, including back-of-house service cores, conference, spaces, and rooftop amenities. These buildings were constructed concurrently with residential towers, increasing logistical complexity across the site. Parking infrastructure was largely integrated into podiums and below-grade levels. This required excavation, dewatering, and reinforced slab construction beneath active building sites. Parking systems were designed to serve multiple uses, including residential, retail, and event traffic, reducing the need for standalone garages. From a construction management perspective, Miami World Center required coordination across dozens of contractors, architects, and engineers. Crane operations, concrete pours, and material deliveries were scheduled to avoid conflicts within a dense, active site. Safety planning was critical due to the proximity of Interstate 395 and ongoing city traffic. The megaproject also included public space construction, such as plazas and pedestrian promenades. These areas required structural support for landscaping, irrigation systems, and integrated lighting. Public realm construction often occurred late in each phase, following heavy structural work. Rising high on the Ethiopian plateau, more than 2 kilometers above sea level, Addis Ababa has always been a city of layers. Old and new, formal and informal, chaotic and alive. But over the past few years, the city has begun to take on an entirely new shape. The Addis Ababa City Corridor and Smart City Project is the centerpiece of that transformation, a sweeping plan to modernize the capital, expand its infrastructure, and create a blueprint for what a 21st century African metropolis can look like. At its heart, the project is about connection. Addis Ababa has grown rapidly, with millions of people moving in from rural regions, but the city's layout and infrastructure never quite kept pace. Roads became crowded, neighborhoods expanded without clear planning, and public services struggled to keep up. The City Corridor Plan aims to tie it all together, a network of modern boulevards, transit routes, and green corridors stretching across the city, designed to integrate housing, commerce, and technology in one continuous urban system. Think of it as both a transportation project and a digital backbone, built to link everything from the city's financial district to its emerging industrial zones. The smart city component is what makes it truly forward-looking. It's not just about widening roads or adding new buildings. It's about embedding intelligence into the fabric of the city itself. Sensor-based traffic management, integrated public data systems, and sustainable utilities that can monitor and adapt in real time. Streetlights powered by solar panels, automated waste collection, water systems that track usage and detect leaks, and transport routes that update dynamically based on congestion. All of these features form part of the vision. Addis Ababa isn't just being expanded, it's being reprogrammed. Alongside the technology, there's also a strong architectural and social vision. The new city corridors are planned to include dedicated pedestrian paths, landscaped parks, and mixed-use developments that bring homes, offices, and public spaces together. Rather than separating zones by function, the aim is to create integrated communities that reduce the need for long commutes and support more sustainable living. It's a response to the sprawl that has defined much of the city's past growth, turning what used to be dusty, disconnected suburbs into modern, connected districts. The construction itself is happening in phases, with local and international teams working together to upgrade transport corridors, build smart infrastructure, and prepare new land for development. It's a massive logistical challenge involving coordination between ministries, tech companies, and city planners, all while trying to minimize disruption in one of Africa's busiest urban centers. But despite the complexity, progress continues steadily, with visible changes appearing year by year. New roads lined with smart lighting, new districts emerging with coordinated urban layouts, and data centers forming the digital core of the city's new systems. What makes the Addis Ababa City Corridor project stand out isn't just its scale, but its symbolism. Ethiopia is positioning itself as a regional leader in technology and infrastructure, and the capital city is its proving ground. The project represents a shift from reactive urban growth to proactive, technology-driven design, an attempt to future-proof a city that's expected to keep growing for decades to come. And when it's complete, Addis Ababa could stand as one of the first truly smart cities on the African continent, built not just to handle its population, but to evolve intelligently alongside it. Just east of Chicago's traditional downtown core, an entire neighborhood has been constructed almost from nothing, making Lakeshore East one of the most significant urban megaprojects in the city's modern history. Built on former rail yards and surface parking lots, the development represents a long-term effort to extend the loop eastward while reconnecting downtown to Lake Michigan. The Lakeshore East site covers roughly 28 acres, bounded by Randolph Street, Lakeshore Drive, and the Chicago River. For much of the 20th century, the land was dominated by Illinois Central Rail infrastructure, service roads, and vacant parcels created by transportation realignments. Large-scale redevelopment became possible only after the decline of rail use and the consolidation of downtown planning efforts in the late 20th century. Formal planning for Lakeshore East began in the 1990s, with a master plan approved to guide phased construction over multiple decades. The development was designed as a high-density, mixed-use neighborhood composed primarily of residential towers supported by retail, office space, hotels, and public amenities. Infrastructure construction was a foundational requirement, including new streets, utility corridors, and a central park system built above active, underground roadways and service structures. One of the defining construction achievements of Lakeshore East is its multi-level design. Much of the neighborhood is built atop a podium that conceals lower-level roads, loading areas, and mechanical systems. This required extensive structural engineering, including reinforced concrete decks capable of supporting high-rise towers while allowing traffic and service access below. At the heart of the project is Lakeshore East Park, a 5-acre landscaped public space completed in the mid-2000s. The park was constructed early in the development timeline to establish a residential anchor and improve land value for surrounding parcels. It includes terraced lawns, water features, and pedestrian paths, all built over underground infrastructure. Vertical construction began in the early 2000s and progressed in phases. Early towers included high-rise residential buildings such as the Lancaster, the Chandler, and the Regatta, which helped establish the neighborhood's residential character. Subsequent phases introduced taller and more architecturally ambitious towers as market demand increased. One of the most prominent structures in Lakeshore East is the Aqua Tower, completed in 2009. Its mixed-use program includes residential units, hotel rooms, and retail space. The tower's construction required complex formwork and balcony systems due to its non-repetitive floor plate design. Aqua became a visual landmark and signaled the neighborhood's arrival as a major component of Chicago's skyline. Other major towers followed, including the Blue Cross Blue Shield Tower, completed in the late 2000s, which added significant office space to the area. This building required integration with existing lower-level infrastructure and direct connections to surrounding streets and transit access points. Residential construction continued through the 2010s with towers such as Coast, Tides, Cascade, and Vista. Vista, completed in the early 2020s, is one of the tallest residential buildings in the world and marked the near completion of the neighborhood's original master plan. Its construction involved deep foundations, high-strength concrete, and extended crane operations due to its height and proximity to Lakeshore Drive. From a timeline perspective, Lakeshore East has been under active construction for more than 2 decades. While the majority of major towers are now complete, the development is not entirely finished. Remaining parcels are reserved for future buildings, and incremental construction is expected to continue into the late 2020s as market conditions allow.
Sometimes, the ground beneath a project tells its own story. For Suvarnabhumi Airport, That story began in the wetlands east of Bangkok, a flood-prone expanse known as Nong Neu Hao, or Cobra Swamp. Turning that swamp into the busiest aviation gateway in Thailand required not just engineering, but imagination on an almost mythic scale. Before the first beam could be raised, the land had to be tamed. Crews moved in with heavy machinery to carry out one of the most extensive ground stabilization efforts ever undertaken in Southeast Asia. The saturated, unstable soil demanded deep foundations, and tens of thousands of concrete piles were driven deep into the ground to support the immense weight of the terminal and its associated infrastructure. This foundational work took years, but it was critical. It was the invisible backbone that would allow the entire project to stand. As soon as the earth was secured, the race to construct the terminal complex began. At the center of the airport's design was the main passenger terminal, a behemoth of steel and glass that, when completed, ranked among the largest in the world under a single continuous roof. The architecture, sleek, curving, and inspired by Thai aesthetics, was as much an engineering feat as it was a visual statement. Erecting its monumental roof structure required custom fabricated trusses and steel arches, assembled on site with millimeter-level precision. These components weren't just massive, they were complex, with each one shaped to accommodate the terminal's signature wave-like profile. Teams worked in coordinated shifts around the clock, craning sections into place, welding, securing, and enclosing vast sections of the structure in a construction ballet that had to hit precise deadlines despite Bangkok's oppressive heat and monsoon rains. Logistically, the site was a challenge. Located more than 25 kilometers from the city center, every piece of equipment, every shipment of materials, had to be routed through carefully orchestrated supply chains. Specialized components, including miles of glass paneling and advanced HVAC systems, were brought in from around the world and integrated into a site that was changing daily. The baggage handling system alone required its own sub-project, spanning multiple levels and kilometers of track, sensors, and software. Even beneath the polished floors and soaring ceilings, the airport's skeleton was a dense network of mechanical systems, each one installed during a phase of construction that had to proceed without disrupting others. While much of the international spotlight shone on the passenger terminal, the runways were no less impressive. Constructed with precision, the dual runways were laid with reinforced concrete to handle heavy aircraft movements, and their drainage systems were meticulously engineered to mitigate the flood risks of the region. Massive underground water management channels and pumping systems were embedded throughout the airport's footprint, ensuring operational continuity even during Thailand's intense rainy season. Control towers, fire stations, maintenance hangars, all of it had to rise in synchronization, each piece playing a critical role in the final orchestration. In the final stretch of construction, coordination became paramount. Hundreds of contractors, thousands of workers, and dozens of subcontracted firms had to bring their work together into a seamless whole. Testing and commissioning were conducted on an enormous scale. Fire suppression systems, electrical grids, telecommunications, lighting, signage, all had to function flawlessly before a single flight could depart. And despite political upheavals and public scrutiny, the airport opened to commercial service with a sense of scale and ambition that left little doubt. This wasn't just a new airport. It was a milestone in Thailand's infrastructure history.
Long before Miami's skyline signaled its rise as a global city, the expansion of Port Miami and its tunnel interchanges quietly re-engineered the region's economic foundation through one of the most consequential infrastructure megaprojects in the county's history. Port Miami, located on Dodge Island in Biscayne Bay, underwent a coordinated expansion program during the late 2000s and early 2010s, aimed at transforming the port into a post-Panamax global trade hub. This effort combined portside construction, navigational improvements, and highway-grade tunnel interchanges into a single integrated mega-project. The goal was to remove physical, maritime, and logistical constraints that limited cargo growth while separating freight movement from downtown Miami's surface streets. One of the earliest and most critical construction components was the deepening of the port's main navigation channel. Prior to expansion, the channel depth restricted access for larger container vessels. Dredging operations began in the early 2010s and involved removing millions of cubic yards of material from Biscayne Bay to achieve a depth of approximately 50 to 52 feet. This work was completed in 2015, timed to coincide with the expanded Panama Canal, allowing Port Miami to receive fully loaded post-Panamax container ships for the first time. On NAS, Dodge Island itself, extensive terminal reconstruction took place in parallel with dredging. Older cargo berths were demolished and rebuilt with reinforced concrete wharves capable of supporting heavier cranes and higher container loads. New gantry cranes, some of the largest in the world at the time of installation, were erected on reinforced rail systems embedded into the key structure. Yard areas were regraded and paved to accommodate automated container handling equipment and higher stacking densities. Utility infrastructure beneath the port was also rebuilt. This included new electrical substations, stormwater drainage systems, fuel distribution lines, and communications networks designed to support modern terminal operations. These upgrades were completed incrementally to avoid disrupting ongoing cargo and cruise activity, requiring phased construction zones across the island. The landside component of the expansion centered on the Port of Miami Tunnel and its highway interchanges, which together form the port's primary freight access system. Construction of the tunnel began in 2010 and was coordinated directly with port expansion schedules. The tunnel consists of two submerged roadway tubes connecting Dodge Island to Watson Island, bypassing downtown Miami entirely. Equally significant were the tunnel interchanges themselves. On the mainland side, major roadway reconstruction was required to tie the tunnel directly into Interstate 395 and Interstate 95. This involved building new elevated ramps, retaining walls, and transition structures capable of handling heavy truck volumes at highway speeds. Existing roadways were demolished and realigned, with traffic maintained throughout construction using temporary detours and phased lane shifts. On the port side, Dodge Island underwent extensive reconfiguration to integrate tunnel portals with internal port circulation. New access roads were built, grade separations installed, and security checkpoints relocated to streamline truck movement. These changes allowed cargo vehicles to enter and exit the port without crossing cruise passenger traffic, significantly improving operational efficiency and safety. The tunnel excavation itself was completed in 2013, but the interchange construction and systems integration extended into 2014. The full tunnel and interchange system opened to traffic in August 2014, marking a major milestone in the port expansion timeline. From that point forward, thousands of trucks per day were rerouted away from downtown Miami streets and directly onto the interstate network. The expansion program also included rail infrastructure improvements. Port Miami's on-dock rail connection was rehabilitated and reactivated, linking the port directly to Florida East Coast railway lines. Track upgrades, switching yards, and loading areas were constructed to enable intermodal freight transfer, reducing dependence on trucking for long-haul cargo movement. In the context of Miami's biggest megaprojects, the Port Miami expansion and tunnel interchanges differ from high-rise developments by operating as a systems-level transformation. The project did not create a single landmark structure, but instead rebuilt the physical processes that allow the city to function as a logistics hub. Its completion aligned with other regional megaprojects, including airport cargo expansion and downtown redevelopment, forming an interconnected infrastructure network. Down on the shores of the Red Sea, where the old port city of Jeddah stretches out between desert and water, two enormous projects are quietly redrawing the map: Jeddah Central and Jeddah Economic City. Together, they represent a vision of transformation unlike anything the city has seen before, turning this historic gateway into a modern global hub for business, culture, and tourism. What makes these developments remarkable isn't just their scale, but the way they weave old and new, ambition and heritage, into something that feels distinctly Saudi, yet unmistakably international. Jeddah Central sits right in the heart of the city, taking over more than 5 square kilometers of waterfront that once housed the old desalination plant and underused industrial land. It's being reinvented as a new downtown, built around a sweeping marina and a waterfront district lined with cultural landmarks, residential towers, and entertainment spaces. The master plan revolves around 4 main landmarks: a sports stadium, an oceanarium, an opera house, and a museum, all designed to anchor Jeddah's identity as a cultural and leisure destination. Around them will rise luxury hotels, office towers, parks and promenades, all connected by shaded walkways and open public spaces, meant to bring life back to the seafront. But this isn't just about aesthetics. The project's layout is designed around sustainability and smart urbanism, integrating renewable energy, green transport systems, and water recycling technologies suited to the coastal climate. It's a major shift for Jeddah, which has long struggled with congestion and uneven urban growth. The plan envisions a livable, walkable downtown that balances modernity with comfort, turning the Red Sea coast into a showcase for the new Saudi lifestyle that's emerging under the country's Vision 2030 framework. The idea is to create not just buildings, but experiences, places where art, commerce, and everyday life blend seamlessly. A short distance to the north, Jeddah Economic City takes that ambition and scales it up to a global level. This is the site of the Jeddah Tower, the skyscraper that aims to surpass 1 kilometer in height and become the tallest building in the world. The tower is the centerpiece of a vast mixed-use development covering more than 50 square kilometers, designed to serve as a new economic hub for trade, finance, and innovation. When complete, Jeddah Economic City will have residential neighborhoods, educational institutions, business districts, and green open spaces all linked together by advanced infrastructure and digital systems. The city's design places a strong focus on integration with the wider region. Ports, highways, and logistics corridors will tie it directly into the national network that connects Jeddah to Makkah, Medina, and eventually NEOM, farther north. In many ways, Jeddah Economic City represents the country's broader push to diversify its economy beyond oil, creating new industries that can attract global investment and talent. Taken together, Jeddah Central and Jeddah Economic City show 2 faces of Saudi Arabia's urban transformation. One is cultural and civic, centered on lifestyle and heritage. The other is economic and technological, reaching for the future through engineering and ambition. Both are shaping a new identity for Jeddah, a city that once served as the gateway for pilgrims, now evolving into a gateway for ideas, enterprise, and modern urban life along the edge of the Red Sea. Beneath Chicago's streets, rivers, and neighborhoods lies one of the largest underground civil engineering systems ever built, a mega project whose scale rivals any visible skyscraper or transit expansion in the city. The Tunnel and Reservoir Plan, commonly known as TARP or the Chicago Deep Tunnel, is a decades-long infrastructure program designed to control flooding, reduce sewer overflows, and protect regional waterways. The origins of TARP trace back to the mid-20th century when rapid urban growth combined stormwater and sewage into a single system that frequently overwhelmed treatment plants. Heavy rainfall routinely forced untreated wastewater into the Chicago River system and Lake Michigan. Planning for a permanent solution began in the 1960s, with construction formally launching in 1975 under the oversight of the Metropolitan Water Reclamation District of Greater Chicago. The core of the project consists of more than 100 miles of deep rock tunnels excavated between 150 and 300 feet below ground. These tunnels range from 9 to over 30 feet in diameter and were bored through solid dolomite bedrock using tunnel boring machines customized for long-duration, high-pressure excavation. Construction occurred in phases over several decades, with tunneling largely completed by the early 2000s. The tunnels function as massive underground storage conduits. During storms, combined sewage is diverted from surface sewers into the deep tunnel network, preventing street flooding and uncontrolled discharges into waterways. Once storms pass, the stored water is gradually pumped to treatment plants for processing. This operational strategy required the construction of dozens of drop shafts, some wider than 30 feet, and extending hundreds of feet downward, connecting surface infrastructure to the tunnel system. A second major component of TARP is its reservoir system, which represents the most visible and recent phase of construction. These reservoirs were designed to provide additional storage capacity beyond the tunnels. The largest of these is the Thornton Composite Reservoir, built within a former limestone quarry south of the city. Construction began in the late 1990s, with phased completion allowing partial operation before the full reservoir was finished. When fully complete, Thornton provides over 7 billion gallons of storage, making it one of the largest stormwater reservoirs in the world. Additional reservoirs include the McCook Reservoir in western Cook County. This facility has been constructed in stages, with the first phase becoming operational in the late 2010s. Full completion, including its second major stage, is scheduled for the mid-2020s. Once finished, McCook will add approximately 10 billion gallons of combined stormwater and sewage storage capacity to the system, significantly increasing flood protection for large portions of Chicago and surrounding suburbs. Along a former industrial corridor stretching between Lincoln Park and Bucktown, one of Chicago's most ambitious redevelopment megaprojects has been planned on land that sat underutilized for decades. Lincoln Yards is a proposed large-scale, mixed-use development intended to transform roughly 53 acres along the north branch of the Chicago River into a new urban district, combining residential, commercial, infrastructure, and public space construction. The site historically housed steel mills, manufacturing plants, and later, large-scale storage and light industrial uses. Much of the land required extensive environmental remediation due to contamination from its industrial past. Preparatory work over the past several years has focused on soil cleanup, demolition of remaining industrial structures, and riverbank stabilization, which represent the earliest construction-related activities tied to the project.
Amid the swirling dust and sun-baked plains of northern Egypt, where the echoes of antiquity still hum beneath the surface, a different kind of monument began to rise in the 20th century. Not one, carved from stone, but cast in concrete and steel. Cairo International Airport was conceived as Egypt's primary portal to the modern world, a replacement for the aging Al-Mazah Airport that could handle the soaring demands of commercial aviation in a capital rapidly expanding in population, influence, and ambition. From its inception, the project was steeped in logistical complexity, shaped by the challenges of working in a desert environment while tethered to the ambitions of a globalizing era. The early phases of construction focused on establishing the core infrastructure that would serve as the foundation for decades of layered growth. Located northeast of central Cairo, the site had to be fully excavated, graded, and serviced with basic utilities in an area that, at the time, lacked deep infrastructure. Massive swaths of earth were moved, and early work involved laying vast concrete aprons and taxiways capable of withstanding the punishing heat and seasonal extremes of the region. The soil conditions, arid and loosely compacted, required specialized engineering techniques to ensure long-term stability. Foundations were reinforced with deep footings and treated aggregate layers to mitigate shifting and cracking under the relentless Egyptian sun. Terminal construction began with a modular approach, an intentional strategy designed to facilitate future expansion without disrupting operations. Terminal 1, known in its early form as the Old Airport, was built with broad, open-plan halls supported by a reinforced concrete frame and long-span steel beams. The design prioritized resilience over aesthetics, focusing on airflow, structural simplicity, and load-bearing efficiency. Glass curtain walls and shading systems were introduced to reduce thermal gain while still allowing for natural light, crucial in a location where daytime temperatures often soared. As aviation volumes increased, the terminal underwent multiple expansion campaigns, each requiring retrofitting older structures with newer systems for baggage handling, ventilation, and fire safety, all while keeping the terminal partially operational. The addition of Terminals 2 and 3 marked a significant evolution in construction philosophy. Terminal 2, originally completed decades ago, eventually underwent a complete overhaul to bring it in line with international standards. This reconstruction was a feat of surgical engineering. The original frame was selectively demolished, and new sections were grafted into the existing structure. Contractors worked in tight, active zones, reinforcing aging concrete, integrating new seismic protections, and threading miles of electrical, plumbing, and HVAC lines through spaces never designed to hold them. Terminal 3, on the other hand, was a clean slate, constructed from the ground up as a state-of-the-art facility to accommodate wide-body aircraft and higher passenger volumes. Its frame was built from high-strength concrete and a steel roof truss system, supporting a terminal footprint that included dual-level departure and arrival flows, jet bridge systems, and a matrix of automated luggage belts built into a multi-tiered substructure. Beyond the terminals, Cairo's runways demanded careful engineering. Laid in parallel orientations to optimize wind handling and maximize simultaneous movements, the runways were constructed with high-durability concrete overlays and embedded lighting systems for all-weather operations. Groundwork involved excavation and subgrade stabilization across thousands of linear meters, requiring constant calibration to maintain level grading and load-bearing integrity. Runway expansions had to be synchronized with radar installations, air traffic control upgrades, and expanded taxiway systems to manage growing traffic without compromising safety or efficiency. Meanwhile, auxiliary construction, parking decks, maintenance hangars, fuel farms, and cargo facilities developed in parallel. Each support system required its own logistical plan, from fuel pipeline installations and fire suppression systems to cold storage zones for cargo handling. The cumulative effect was a sprawling, highly compartmentalized aviation complex whose every square meter had to be engineered for durability, redundancy, and heat resilience.
Beneath Biscayne Bay, hidden from the skyline that defines Miami's megaproject boom, the Port of Miami Tunnel represents one of the most complex and consequential infrastructure projects ever built in South Florida. The Port of Miami Tunnel was designed to directly connect Dodge Island, home to Port Miami, with the interstate highway system creating a dedicated underground freight corridor between the port and Interstate 395 and Interstate 95. Before the tunnel, cargo trucks were forced to move through downtown Miami streets, creating chronic congestion, safety issues, and delays that constrained the port's growth. The tunnel fundamentally restructured how goods move through the city, making it a critical component of Miami's broader megaproject transformation. Planning for the tunnel began decades before construction, with serious development efforts accelerating in the early 2000s as Port Miami expanded into a major global cargo and cruise hub. Construction officially began in 2010 after years of environmental review, financing negotiations, and engineering studies. The project was delivered through a public-private partnership, an uncommon approach at the time for U.S. transportation megaprojects, involving the Florida Department of Transportation and a private concessionaire responsible for design, construction, financing, and long-term operation. The construction scope centered on 2 parallel tunnel tubes, each approximately 3,900 feet long, bored beneath Biscayne Bay. The tunnels were excavated using a massive tunnel boring machine specifically designed to operate in Miami's challenging geology, which consists of porous limestone, sand, and a high water table. The tunnel boring machine, weighing thousands of tons, was launched from Watson Island and advanced underwater toward Dodge Island, cutting through bedrock while simultaneously installing precast concrete liner segments to stabilize the tunnel walls. Excavation operations required continuous groundwater management and precise pressure control to prevent collapse or water intrusion. The tunnel alignment passed beneath active shipping channels, requiring careful coordination to avoid disrupting port operations and marine traffic. Spoil material removed during tunneling was transported and processed without interfering with surrounding urban and maritime infrastructure. In addition to the underwater tunnels, the project included extensive cut and cover construction on both ends. On Watson Island and Dodge Island, large access portals were excavated, requiring dewatering systems, retaining walls, and deep foundations to support the tunnel entrances. New roadway interchanges were built to connect the tunnel directly to I-395, eliminating truck traffic through surface streets in downtown Miami. Construction also included advanced ventilation buildings, fire suppression systems, emergency cross passages between tunnel tubes, and real-time monitoring systems. These safety features were essential to meet federal highway tunnel standards and ensure continuous operation in a hurricane-prone region. The tunnel was engineered to withstand storm surge, seismic forces, and long-term exposure to saltwater conditions. The project faced multiple technical and schedule challenges during construction. Delays occurred due to mechanical issues with the tunnel boring machine, groundwater infiltration events, and the complexity of working beneath an active port and bay. Despite these challenges, tunneling was completed in 2013, marking one of the most technically demanding phases of the project. Following structural completion, several years were dedicated to roadway finishing, systems installation, testing and commissioning, ventilation, lighting, traffic control, and emergency systems underwent extensive testing before the tunnel was open to traffic. The Port of Miami Tunnel officially opened in August 2014, completing a construction timeline of roughly 4 years. Within the context of Miami's biggest mega projects, the Port of Miami Tunnel stands apart from high-rise developments like Panorama Tower or Brickell City Center. Rather than reshaping the skyline, it reshaped the city's logistical foundation. By removing thousands of trucks per day from downtown streets, the tunnel enabled parallel megaprojects in residential, commercial, and cultural development to proceed without freight congestion, limiting growth. In the vast emptiness of northwestern Saudi Arabia, where desert and mountains stretch endlessly under the sun, a line of glass and steel is being drawn across the landscape. A city unlike any that has ever been built before. It's called The Line, and it forms the central vision of NEOM, a futuristic megaproject meant to redefine what urban living can be in the 21st century. The idea sounds almost impossible at first, a city that isn't sprawling outward, but extending straight for hundreds of kilometers, only 200 meters wide, yet home to millions of people. But that's exactly the scale of ambition Saudi Arabia is pursuing, nothing less than the reinvention of civilization itself. The concept behind the line begins with simplicity. Instead of spreading a city outward in all directions, it compresses everything into a single linear corridor that runs through desert valleys and over coastal plains. The two mirrored walls of the city rise more than 400 meters, enclosing a narrow interior where people will live, work, and travel vertically rather than horizontally. The structure is designed to function as a continuous vertical metropolis, where everything, from housing and offices to schools, parks, and public transit, is stacked efficiently inside a climate-controlled environment. At its core, the line is meant to operate without cars, roads, or traditional streets. Instead, it relies on a high-speed underground transport system that can move people from end to end in minutes. The idea is that every daily need, groceries, healthcare, education, recreation, should be within a 5-minute walk. By eliminating cars and long commutes, the designers aim to create a city where time is reclaimed for people, where nature and urban life coexist without one overwhelming the other. Sustainability sits at the center of the entire plan. The line is being built to run entirely on renewable energy, primarily from solar and wind power, and its compact footprint minimizes land use and environmental impact. The vertical design allows the surrounding desert and mountains to remain untouched, preserving natural ecosystems, while housing millions of people in a fraction of the space that a normal city would require. The structure's mirrored facade isn't just aesthetic. It reflects sunlight to reduce heat absorption and helps control the city's internal temperature. Engineering something of this magnitude pushes the boundaries of what's physically possible. The foundation requires precision construction over uneven terrain, and the structural demands of building two continuous walls hundreds of meters high across such distances are immense. The integration of transportation systems, data networks, energy grids, and vertical living spaces has to function seamlessly for the vision to work. Every part of the city will be monitored and managed through AI-driven systems, adjusting lighting, temperature, and logistics dynamically to optimize efficiency and comfort. The line also represents a broader idea about the future of Saudi Arabia. It's not just a mega project, it's a statement of national transformation. It reflects the country's drive to diversify beyond oil, to attract technology, investment, and global talent, and to present itself as a center of innovation. For the government, the line is both an economic experiment and a symbol of ambition, projecting the image of a nation willing to take risk to shape the next century. Whether it succeeds or not, the line is already changing the conversation about what cities can be. It's forcing engineers, architects, and planners around the world to imagine new forms of living, new ways of organizing society, and new relationships between humans and the environment. In the middle of the desert, a city that runs in a straight line may seem improbable, but that's precisely the point. It's a bet on imagination and on the belief that the future doesn't have to look anything like the past. South of Chicago's Loop and directly east of Grant Park, one of the most ambitious and complex megaprojects ever proposed in the city is planned not on open land, but above active rail infrastructure. One Central Chicago is a large-scale, long-term development proposal centered on constructing a massive transit-oriented platform over the Metra Electric Rail Yard near Soldier Field, redefining how Chicago approaches air rights development. The core of the One Central proposal is the construction of a multi-level structural deck spanning more than 30 acres of rail lines. This deck would serve as the foundation for an entirely new neighborhood, allowing vertical development to rise above existing transportation corridors without displacing them. The engineering challenge is central to the project, requiring heavy load-bearing caissons, vibration isolation systems, and phased construction that allows uninterrupted rail operations below. The project is structured around a new central transit hub, envisioned as one of the largest in the Midwest. The hub would integrate Metro electric trains, CTA bus services, potential future rail connections, and pedestrian and bicycle networks into a single, consolidated station. Transit infrastructure is planned as the first major construction phase, establishing the structural deck and station facilities before any private buildings rise above. One Central is approved conceptually as a multi-decade development, not a single construction effort. The full build-out is projected to extend into the 2040s, with individual phases dependent on financing, tenant demand, and infrastructure funding. Early construction would focus on the deck, transit facilities, and utility systems, a process expected to take several years before vertical development begins. The proposed scale places One Central among the largest megaprojects in Chicago history. At full build-out, the plan allows for millions of square feet of mixed-use development, including residential towers, office space, hotels, academic and research facilities, and cultural venues. Building heights would vary across phases, with some towers reaching high-rise and super-tall classifications, though final designs remain flexible. Infrastructure construction is the defining feature of the project. Beyond the deck itself, One Central requires new roadways, stormwater management systems, electrical substations, and telecommunications networks. Because the site sits between Lake Michigan and downtown, flood resilience and drainage engineering are critical components of the design. Elevated building pads and integrated water management systems are planned to address long-term climate risks. Unlike many Chicago megaprojects, One Central has not yet entered full construction. As of the mid-2020s, the project remains in advanced planning and approval stages, with negotiations focused on public-private partnerships, transit funding, and long-term governance. The project's viability is closely tied to securing funding for the transit hub, which is considered essential to unlocking the value of the surrounding development. The location gives the project strategic importance. It sits between the museum campus, McCormick Place, Soldier Field, and downtown, creating a potential bridge between Chicago's civic core and its convention and entertainment districts. The development would also reconnect neighborhoods long separated by rail infrastructure, using the deck as both a building platform and a public realm. From a construction sequencing standpoint, One Central differs from traditional real estate projects. No single building can proceed independently. Each phase depends on completion of shared structural and transit elements, making coordination and long-term scheduling central to the project's execution. This complexity places One Central closer to infrastructure megaprojects like transit expansions than conventional mixed-use developments.
They didn't just build an airport on the shores of the Black Sea. They carved a new future for a nation out of rock, sea, and ambition. The construction of Istanbul Airport, one of the most audacious infrastructure projects of the 21st century, was not just a matter of civil engineering. It was a national statement, a vision chiseled into existence with relentless speed and almost cinematic scale. From the very first shovel of Earth, this project wasn't designed to follow global aviation standards. It was meant to redefine them. The site itself was a challenge from the start. A mix of former open-pit coal mines, wetlands, and unstable terrain that required millions of cubic meters of earth to be moved, compacted, and stabilized. This wasn't just land reclamation. It was land transformation on a continental scale. Thousands of workers labored around the clock, building not only runways and terminals, but the very ground those structures would stand on. The scale of the terminal alone is staggering. Designed to be the largest under a single roof anywhere on Earth, the main passenger terminal covers over 1 million square meters. Its skeleton is steel, its skin glass and aluminum, but its foundation is poured from unflinching confidence. Every beam, every column was part of a choreography measured in millimeters, but executed at megastructure scale. Construction teams sourced materials from all over Turkey and beyond, fueling a logistical operation that mirrored military precision. Concrete was poured by the ton, and cranes moved like clock hands over the site, some of them among the tallest and most powerful in the world. And at the heart of it all, the project had to maintain momentum in a political and economic climate that was, at times, deeply volatile. Timing was everything. The goal was clear from the start. Open fast, open big. Unlike projects that slowly build up capacity, Istanbul Airport was envisioned to make a splash from day one. That meant building not one, but multiple parallel runways right from the outset, designed to handle hundreds of flights a day with minimal delay. The air traffic control tower, with its sleek, tulip-inspired silhouette, was one of the first structures to rise, signaling the pace and design sophistication the rest of the site would follow. Around it, a spiderweb of service roads, utility tunnels, fuel lines, and drainage systems had to be laid out with unerring accuracy. Every inch of the infrastructure was future-proofed to accommodate the long-term goal. Over 200 million passengers annually once all phases are complete. No corner of this site was spared from overachievement. The cargo facilities were built to rival dedicated freight airports, with massive warehouses and high-speed loading systems constructed at breakneck pace. The runway system, built across 4 phases, was designed not only for volume but for wind, direction optimization, weather resilience, and operational efficiency that could outpace even the world's most established airports. Drainage was a particular challenge, given the area's geography. Massive culverts and underground reservoirs were constructed to manage rainwater and prevent flooding, a vital concern in a place where the sea is never far and the weather can turn swiftly. Even power and data lines were installed with redundancy and scalability in mind, buried deep and routed through protected channels to safeguard against both overload and sabotage. When construction crews finally handed over the keys, what they left behind wasn't just an airport. It was a piece of infrastructure that looked less like a public utility and more like a declaration carved into the earth. The sheer act of building it, under such tight deadlines, across such difficult terrain, and on such a colossal scale, stands as one of the great modern feats of engineering. It's not just what was built, it's how it was done. Quickly, relentlessly, and without blinking in the face of impossible complexity. Tucked just south of downtown Los Angeles, Exposition Park has always been a place of ambition, home to world-class museums, the LA Memorial Coliseum, and the beating heart of the city's cultural and sporting life. But what's unfolding there now isn't just an upgrade. It's a full-scale transformation, timed to align with the arrival of the 2028 Olympic Games. This is the Exposition Park expansion, and it's one of the most concentrated, multi-layered megaprojects happening anywhere in the city. We're talking about more than 100 acres of dense, high-profile development, the kind of space where architecture, infrastructure, landscape, and engineering have to work in seamless coordination, and every inch of it is being reimagined, stitched together into a new kind of urban park, one that blends Olympic-scale sports facilities with civic space, transit access, and cultural presence. At the center of this expansion is the Lucas Museum of Narrative Art, an enormous, fluid, almost spaceship-like structure that defies traditional design logic. Spanning over 300,000 square feet, the building floats above the landscape on concrete pylons, allowing for an uninterrupted park to run beneath it. Engineering that vision into reality meant solving a long list of structural challenges. The museum's form curves and bends with few right angles, requiring a steel skeleton unlike any conventional grid. Every beam had to be custom fabricated. Load paths had to be recalculated from scratch. But that's only one piece. Adjacent to it, new Olympic training facilities are being added in and around the Coliseum, including athlete, housing, high-performance sports labs, and temporary structures built to IOC standards. These aren't off-the-shelf projects. Each facility must meet international competition criteria while being adaptable for post-games public use. That means flexible infrastructure, modular designs that can expand or collapse depending on future needs, and utility corridors capable of serving both a global broadcast event and a local youth sports league. A new mobility hub is also under construction, tightly integrated with the K Line, Crenshaw LAX Line, regional bus service, and pedestrian corridors linking USC, the Natural History Museum, and BMO Stadium. This isn't just about moving people, it's about rethinking access. Engineers are embedding smart traffic systems, ADA upgrades, secure bike lanes, and crowd flow modeling to handle Olympic-scale surges without overwhelming local streets. Then there's the landscape itself. More than 14 acres of new green space are being carved into the existing grid, with bioswales, permeable pavement, and stormwater recycling systems hidden beneath sculpted terrain. Everything is dual purpose. That shaded plaza? It's also an emergency egress route. That rolling hill. It's backfilled over a utilities corridor with seismic isolation joints. Every tree and trail was designed not just for beauty, but for function, cooling microclimates, guiding crowds, and managing runoff during rare but intense LA storms. Beneath the surface, the engineering complexity continues. Utility upgrades, electric, water, fiber, gas, are being laid out like a circulatory system for a future-proof urban core. Crews had to dig and trench with surgical accuracy, often working just inches away from existing structures that couldn't be moved or shut down. Phasing the construction without interrupting events at the Coliseum or the Museum District meant round-the-clock scheduling, heavy prefabrication, and just-in-time delivery logistics.
Set within the dense fabric of downtown Miami, Miami Central represents one of the most complex, privately delivered megaprojects ever completed in the city, combining rail infrastructure, vertical construction, and urban redevelopment into a single coordinated build. Miami Central is a mixed-use, transit-oriented development centered on the southern terminus of Brightline's intercity rail system. The project occupies multiple city blocks between Northwest 1st Avenue and Northwest 6th Street, directly adjacent to Government Center. Planning for Miami Central began in the early 2010s as part of a broader effort to reintroduce intercity passenger rail to Florida, while simultaneously redeveloping underutilized downtown land. Construction officially began around 2014, with early work focused on site preparation, demolition of existing low-rise structures, utility relocation, and rail corridor reconstruction. The project required rebuilding active rail alignments while maintaining freight operations on the Florida East Coast Railway, necessitating phased construction sequencing and temporary track realignments. At the core of Miami Central is the Brightline station, constructed as an elevated rail terminal spanning multiple blocks. The station structure required long-span concrete and steel framing to support train platforms above street level while allowing uninterrupted traffic flow beneath. Platform construction included high-load track slabs, vibration mitigation systems, signaling infrastructure, and integrated safety systems compliant with federal rail standards. Below and around the station, the project incorporated significant structural podium construction. Large transfer slabs were built to distribute loads from residential towers above while accommodating open concourses, retail space, and passenger circulation areas below. This approach allowed rail, pedestrian, and vehicular systems to coexist within a constrained urban footprint. Miami Central includes multiple high-rise towers developed in phases. The first residential towers began vertical construction after the station structure was well underway. These towers required deep foundations and auger-cast piles to manage Miami's soil conditions and groundwater levels. Structural systems used reinforced concrete cores with flat plate floor construction, optimized for residential occupancy and high-rise efficiency. In addition to residential units, Miami Central incorporated office space, hotel components, and retail frontage. Mechanical, electrical, and plumbing systems were designed to operate independently across uses while sharing centralized infrastructure where possible. Loading docks, service corridors, and back-of-house systems were embedded into the lower levels to minimize surface disruption. A defining construction challenge was integrating multiple transportation modes into a single site. Miami Central connects Brightline Intercity Rail, Metro Rail, Metro Mover, Metrobus, and pedestrian networks. Construction included new elevated walkways, platform connections, fare control zones, and vertical circulation systems, linking existing transit infrastructure to newly built spaces. Roadway reconstruction was another major component. Portions of Northwest First Avenue and surrounding streets were rebuilt to accommodate new traffic patterns, curbside loading, and pedestrian access. Streetscape improvements included drainage upgrades, structural decking over rail corridors, and reinforced pavement designed for heavy service vehicles. The timeline of Miami Central unfolded in stages. Rail corridor and station construction progressed between roughly 2014 and 2017. The Brightline station reached functional completion in late 2017, coinciding with the launch of passenger service between Miami and Fort Lauderdale, later extended to West Palm Beach. Full station operations began in early 2018. Residential towers were delivered in phases, with initial buildings completed around 2018 and additional towers finishing in subsequent years. Retail and public spaces opened gradually as tenant build-outs were completed. The project did not conclude with a single completion date, but by the late 2010s, Miami Central was fully operational as a transit hub and mixed-use district. Within the context of Miami's biggest megaprojects, Miami Central stands out for being privately financed and rail-centric. Unlike publicly led infrastructure efforts such as the Port of Miami Tunnel or airport expansions, Miami Central combined transportation infrastructure with real estate development under a single master plan. This approach shifted how large-scale projects could be delivered in Miami's urban core. From a construction management perspective, Miami Central required coordination among rail engineers, vertical construction contractors, transit agencies, and city departments. Work occurred simultaneously above, below, and alongside active transit lines, requiring constant monitoring of settlement, vibration, and structural movement. By the middle of the decade, one of North Texas's earliest soccer-specific stadiums is undergoing a comprehensive reconstruction that places it firmly among Dallas area megaprojects active in 2026. The new Toyota Stadium redevelopment in Frisco represents a multi-year modernization effort focused on structural capacity, revenue generation, climate mitigation, and long-term event flexibility rather than a simple renovation. Toyota Stadium originally opened in 2005, designed for a different era of Major League Soccer and a much smaller regional population. The redevelopment project restructures the existing stadium rather than replacing it, allowing FC Dallas to continue operations while construction advances in carefully sequenced phases. By 2026, the project is deep into its most technically demanding stage, with heavy construction occurring throughout the seating bowl, concourses, and building systems. Construction work during 2026 concentrates on major structural modifications. Entire sections of the lower bowl are being demolished and rebuilt to adjust rake angles, improve sightlines, and support additional vertical loads from new premium levels above. New concrete pours and steel framing are installed in phases to maintain stadium stability, while adjacent areas remain operational. This year also includes reinforcement of existing foundations to meet updated building codes and support heavier roof and canopy systems. One of the most visible construction efforts in 2026 is the installation of expanded canopy structures. These roof elements are designed to significantly increase shaded seating, addressing long-standing heat exposure issues. The canopy construction involves large-span steel trusses, integrated lighting mounts, and future-ready broadcast attachment points. Installation is staged section by section to allow partial stadium use during the soccer season. Premium seating and hospitality spaces dominate interior construction in 2026. New club lounges, lodge boxes, and suites are being built into previously underutilized stadium volume. This requires extensive mechanical and electrical upgrades, including new air handling units, upgraded power distribution rooms, and expanded data infrastructure. Plumbing systems are also being replaced or rerouted to serve higher capacity food and beverage operations. Concourse reconstruction is another major focus in 2026. Existing concourses are being widened, regraded, and reconfigured to improve circulation and accessibility. Vertical transportation systems, including elevators and stairs, are being added or relocated to comply with modern accessibility standards. These changes require careful coordination between demolition crews, concrete teams, and utility installers to avoid service disruptions. Technology infrastructure work accelerates during 2026. Crews are installing new fiber optic backbones, wireless access systems, and security networks throughout the stadium. Dedicated broadcast rooms and control spaces are under construction to support national and international television requirements. These systems are designed to accommodate future tournaments and non-soccer events without additional major retrofits. Outside the stadium bowl, 2026 construction includes the redevelopment of surrounding plazas and entry zones. Pedestrian circulation is being improved through expanded hardscape areas, upgraded lighting, and reworked security screening layouts. These exterior improvements are engineered to support higher peak attendance and year-round events, not just match days. Sustainability measures are integrated into the 2026 construction scope. Lighting systems are being converted to high-efficiency LED fixtures. Water infrastructure is upgraded with low-flow systems, and stormwater management improvements are installed to reduce runoff during heavy rain events. Older materials removed during demolition are being recycled or reused where feasible to reduce construction waste. From a timeline perspective, 2026 represents the midpoint of the redevelopment. Structural and exterior envelope work dominates early and mid-year, while interior build-outs continue into late 2026 and beyond. Some premium areas and upgraded seating sections are expected to open in phases as construction completes, allowing incremental increases in stadium functionality. Major construction activity is scheduled to continue through 2027, with final interior finishes, technology commissioning, and operational testing extending into late 2027. Full project completion is expected between late 2027 and 2028, depending on seasonal construction constraints and event scheduling. The phased delivery approach ensures continuous stadium use while transitioning the facility to its final configuration.